What if the universe isn't just vast, but unfathomably paradoxical? Imagine drifting into sleep while contemplating the very limits of existence, the mind-bending realities that lie just beyond our grasp. This isn't just background noise. It's a cosmic lullaby designed to expand your consciousness while guiding you to a unique, contemplative rest. Let's start with first. Infinite universe paradox. Imagine for a moment that the universe does not end. No walls, no boundaries, no edge where the stars stop shining. Imagine a cosmos that stretches outward without limit, an infinite ocean of galaxies, worlds, and possibilities. Now, if infinity truly exists, then something strange, something unsettling, emerges. Infinity is not just vast. Infinity repeats. Within endless space, patterns cannot remain unique. Just as in an infinite string of numbers, the sequence 123 appears again and again, so too would every possible arrangement of atoms, every possible life, every possible version of you. The paradox strikes here. If the cosmos is infinite, then you are not singular. You are already duplicated, mirrored, replayed across endless horizons. And somewhere out there, another you is listening to these words right now. To understand this deeply, imagine shuffling a deck of cards. With 52 cards, there are about 10 to the power of 68 possible arrangements, an almost unimaginable number. Yet it is still finite. In an infinite universe, if you shuffle for eternity, every single arrangement must appear again, not just once, but infinitely often. The same logic applies to atoms. The arrangement that makes your body, your memories, your loves, your fears, it is just a configuration of particles. If infinity holds, then this configuration recurs. Not one duplicate. Not two. An uncountable ocean of copies, each living the same life, each asking the same questions, each believing itself unique. And yet, the paradox grows stranger. If infinity repeats every possibility, then it also contains variations. There are worlds where you turned left instead of right, where you confessed instead of staying silent, where you lived instead of dying. Every path you could have taken is taken somewhere. Every dream you abandoned breathes somewhere else. Infinity does not only mirror, it expands into all branches. You exist not just in duplication, but in variation, spread across dimensions of choice scattered through infinite space. Imagine a library where every book ever written exists. In an infinite library, not only every book written, but every book that could be written, every possible combination of letters, every alternate ending, every story. Our universe, if infinite, is that library, but with lives instead of books. The unsettling weight of this idea is not only that duplicates exist, but that uniqueness itself dissolves. The face you see in the mirror, the voice you believe only you carry, the private memories you hold, none of them are truly singular in infinity. Somewhere out there, someone else holds them too. Perhaps on a planet almost identical to Earth, circling a sun almost identical to ours, a person sits, blinking, convinced of their individuality, unaware they are but one page in a book of endless repetition. What does this mean for meaning itself? If every choice repeats, if every life is lived endlessly, then does life lose its gravity, or does it gain more? Let us go deeper. Imagine walking down a street. The cobblestones under your feet, the sound of a bird overhead, the passing glance of a stranger. All of these are configurations of particles. In an infinite universe, this exact walk must happen again, not just on another Earth-like planet, but in infinitely many of them. The same bird, the same glance, the same breath. The paradox whispers, are you walking this street for the first time, or the trillionth? Does it matter? The uniqueness of the moment collapses under infinity, yet the moment itself still feels real. This tension, between the feeling of singularity and the reality of repetition, is the heart of the infinite universe paradox. And it is not just philosophy. Physics itself brushes against this truth. Cosmologists speak of the observable universe, the bubble of space we can see, about 93 billion light-years across. But beyond that, we do not know. If space is infinite, then the number of possible arrangements of matter within each observable bubble is finite. That means, statistically, that your observable universe must repeat. Somewhere, unimaginably far away, there is another bubble where every star, every galaxy, every planet is arranged exactly as here. And somewhere beyond that, a bubble where things diverge just slightly, where you were born 1 second earlier or never born at all. Think about the emotional consequence of this. Every regret you carry, every "what if" you whisper to yourself, there is a version of you who did the opposite. They live that life right now. Every heartbreak has its alternate ending. Every failure its alternate triumph. But you cannot reach them. Infinity guarantees existence, but not connection. You are locked into your thread, while infinite other threads play out in parallel, unreachable, untouchable, unknowable. That is both a comfort and a torment. Comfort, because nothing was ever truly lost. Torment, because you will never touch those versions of yourself. Let us test this with a simple example. Imagine a coin tossed infinitely. Every sequence of heads and tails will eventually occur. Somewhere in that infinity is the exact sequence of your life, encoded in binary. Birth as heads, death as tails, each moment as a flip. That sequence will appear not once but endlessly, embedded in the chaos. So too are all other sequences. The infinite universe paradox says, you are not an accident of one toss, but part of an endless recurrence of tosses. The staggering consequence is that you cannot be erased. Infinity repeats you forever. Even if Earth dies, even if galaxies collapse, somewhere else the pattern begins again. Your life is not fragile. It is indestructible through repetition. But here lies the deepest question. If everything repeats, what then is the purpose of living this version? If you will exist again and again, does this moment lose its urgency? Or does it demand more reverence, precisely because it will be repeated? Nietzsche once asked if you would live your life again eternally. The infinite universe says you already are. Every breath you take is taken endlessly. Every pain and joy reverberates forever. You are not living a life that will vanish. You are living a life that is written across infinity. And yet, there is still mystery. For though infinity demands repetition, you cannot feel the other versions of yourself. You cannot recall their choices, their joys, their sorrows. You are sealed in the cage of your own perspective, which means that, for you, this moment is still unique. Yes, infinite copies exist, but you are the one living this thread. Your pain is yours, your joy is yours, your love is yours, no matter how many mirrors reflect it elsewhere. The paradox does not dissolve meaning, it sharpens it. Infinity does not cancel your life. It multiplies it. But your awareness of this moment remains singular. And that is the mystery, to be infinite and unique at once. So when you look up at the night sky, remember, you are not just staring into distance, but into mirrors. Behind those stars may be other yous, other lives, other versions replaying the same script. The cosmos may be infinite, but the experience of being you right now remains irreplaceable. That is the paradox we cannot escape. You are everywhere, and yet you are only here. Heat-death dilemma. Imagine a future so distant that the very concept of future becomes meaningless. Stars have burned out, galaxies drift apart in unreachable silence, and every particle has spread so thin across the cosmos that nothing interacts, nothing collides, nothing changes. This is the scenario physicists call the heat death of the universe, a vision where expansion stretches reality into a cold, endless stillness. And yet, here lies the paradox. If time is the measure of change, then what does it mean to speak of time when all change has ceased? If everything is frozen in eternal equilibrium, does time itself still tick forward, or does it dissolve into irrelevance, like a clock that continues to run in a room where no one exists to hear its ticking? The dilemma is that stillness can only be described against the backdrop of motion. Silence only makes sense because once there was sound. To say, "nothing happens," requires the assumption that time still exists to measure the absence of events. But if entropy has reached its absolute maximum, if every difference between states has flattened, then there is no longer any before or after. The very grammar of time collapses, leaving us with an eternity that cannot be experienced, because experience itself requires difference. In this way, the heat death is not just an end of stars, but an end of story. No beginning, no climax, no conclusion. Just a vast, eternal, irreversible pause. To imagine this deeply, consider your own life. You mark your days through change, the rise and fall of the sun, the beating of your heart, the growth of your body, the decay of moments into memory. Time feels real because things evolve. Now imagine if nothing within you or around you changed. Imagine every atom in your body perfectly balanced, no metabolism, no heartbeat, no decay. Even if you existed, you could not tell one moment from the next. You could not say, "I am here," and then, "I am still here," because the act of recognizing persistence itself demands contrast. Without change, consciousness cannot exist. Without consciousness, what does it mean to call something time? Cosmologists debate whether heat death is our true destiny. The universe is expanding, and evidence shows that expansion is accelerating, driven by dark energy. If this continues infinitely, galaxies will not just drift, they will race apart faster than light, tearing all bonds of matter until nothing remains but isolated particles diffused across unimaginable gulfs of emptiness. Every black hole will evaporate into Hawking radiation. Every atom will eventually decay. All structure will vanish. And in this infinite dispersal, entropy reaches its peak. But here is the profound twist. Entropy is not chaos. Entropy is balance. It is the state where everything has spread out so evenly that nothing further can happen. Heat death is not fire but silence. Not burning but cooling. Not violence but perfect symmetry. And yet, the paradox grows darker. If time itself requires change, then after the heat death, does time simply stop, or does it keep going endlessly in a void of nothing happening? Some physicists suggest that even in maximum entropy, quantum fluctuations could randomly spark new events, perhaps even new universes. Others argue that such fluctuations would themselves require a meaningful arrow of time, which may no longer exist. The question becomes inescapable. If no one is there to measure, no change to record, is time still real? Or does it dissolve into an illusion, revealed as nothing more than the language of motion? This dilemma is not only cosmic, it is existential. Think of how we experience boredom. When you sit in a silent room for hours with nothing to do, time itself begins to feel heavy, distorted, almost absent. Minutes stretch like hours. But the very awareness of that stretching comes from the contrast between expectation and stillness. If boredom could be extended infinitely, with no contrast, eventually you would lose all sense of time. You would dissolve into it. The heat death of the cosmos is boredom at an absolute scale, a boredom so total that the very possibility of noticing has disappeared. And yet, there is a strange comfort in this vision. For if time ends in stillness, then it may mean that suffering ends as well. No more decay, no more violence, no more unfinished longing. Just equilibrium, where every possibility has already played out and settled into silence. To some, this is terrifying, the loss of all narrative. To others, it is peaceful, the final release from struggle. The paradox is that our minds cannot help but picture this stillness as an eternity, a never-ending stretch of frozen time. But in truth, it may not be eternity at all. It may simply be the absence of time itself. Not an infinite continuation, but the removal of the canvas upon which continuation is painted. Let us take another example. Imagine reading a book. Each page turned is a moment, each sentence a change. The story exists because of difference between one line and the next. Now imagine reaching the end of the book, and instead of closing it, you stare at the last page forever. Nothing more is written, nothing more is revealed. The book is not infinite, it has stopped. You may keep staring, but the story has ended. The heat death of the universe is like this, the final page, with no sequel. We think of it as endless, but perhaps it is not endless at all. Perhaps it is simply over. So where does that leave us? The heat-death dilemma shows us that time, the very thing we take for granted as the most fundamental dimension of existence, is not an absolute container. It is dependent on change, on events, on entropy. And when entropy has run its course, time itself may fade, leaving not infinity, but something stranger, silence without duration. The true challenge is that our language, our imagination, our very brains are built within the fabric of time. To imagine its absence is like asking a fish to imagine the absence of water. We cannot do it fully. We can only circle it with paradox, pointing toward a horizon we cannot cross. Perhaps that is the ultimate lesson of the heat-death dilemma, that the universe itself may not end in flame or collapse, but in a riddle. A state that is not life, not death, not time, not eternity. A place beyond description, because description requires sequence, and sequence requires time. In that sense, the universe may one day reach a silence so profound that not even silence remains. A stillness so complete that even the word still has lost its meaning. And if we dare to ask whether this stillness lasts forever, we already fall into error, because forever is itself a measure of time. The heat-death is not the eternity of time, it is the erasure of time. And in that erasure lies a mystery so absolute, it may be the final paradox we will never solve. Black hole information paradox. Imagine standing at the edge of the greatest mystery in the cosmos, a black hole. A region so dense, so powerful, that even light itself cannot escape its grasp. To the human eye, it looks like a void, a tear in the fabric of reality. And yet, within this darkness lies one of the most profound paradoxes science has ever faced, the black hole information paradox. At its core, the question seems simple. When matter falls into a black hole, what happens to the information it carries? The atoms, the particles, the arrangement of energy and matter, all of it encodes information about the universe. Quantum mechanics tells us that information can never be destroyed. It can be scrambled, distorted, transformed, but it cannot simply vanish. Yet general relativity, the law that governs gravity and black holes, suggests the opposite. It says that once something crosses the event horizon, the point of no return, it is gone forever, erased from our universe. Here, reality fractures into two irreconcilable truths, and the paradox emerges. To understand the gravity of this conflict, imagine burning a book. On the surface, it looks like the information in the words is destroyed. But physics tells us it isn't. The smoke, the ash, the heat, the light radiating out all carry fragments of the book's original state. In theory, if one had infinite precision and knowledge, the original could be reconstructed from those remnants. That is quantum law. Information may be hidden, but it is never gone. But now take that same book and throw it into a black hole. According to Einstein's general relativity, once it crosses the horizon, no trace can ever be retrieved. The words, the ink, the pages, all swallowed into silence. This is not just destruction. It is erasure at the fundamental level, and that, according to quantum mechanics, should be impossible. Stephen Hawking's work in the 1970s added fuel to this paradox. He discovered that black holes are not eternal prisons. Instead, they radiate tiny amounts of energy, a phenomenon we now call Hawking radiation. Over immense stretches of time, a black hole will slowly leak away its mass, evaporating into nothingness. But here's the problem. Hawking radiation is purely thermal. It carries no information about what originally fell in. If this is true, then when the black hole finally vanishes, so does all the information it once held. Imagine the history of stars, planets, entire civilizations being swallowed, only to have their stories vanish into meaningless heat. The universe, in this picture, erases its own memory. But if information is lost, quantum mechanics collapses. The very foundation of physics breaks. The laws of cause and effect, the consistency of time, even the possibility of science itself, all of it becomes questionable. The paradox is not a small crack. It is a tear that could unravel the entire fabric of understanding. Physicists have spent decades wrestling with this. Some propose that information is somehow encoded on the surface of the event horizon itself, like a cosmic hologram. This idea, known as the holographic principle, suggests that the three-dimensional contents of the black hole might be represented on its two-dimensional boundary. Imagine a painting so detailed that every brushstroke encodes the history of an entire universe, flattened onto the horizon of the black hole. Others argue that Hawking radiation is not truly random, that it might subtly carry the information out, encoded in ways we don't yet understand. If true, then black holes would not destroy information but merely scramble it beyond recognition, like a locked safe whose combination we have not discovered. Another radical idea is the concept of black hole firewalls, searing walls of energy at the event horizon that might burn away infalling matter, preserving information in violent flashes before it disappears. But these theories themselves clash with other sacred principles of physics, forcing us deeper into paradox. To grasp the intensity of this dilemma, consider an example. Imagine you, right now, falling into a black hole. To an outside observer, time would appear to slow down as you approach the event horizon. Your body would stretch, thin, and freeze in place, your last light forever hanging on the edge. From your perspective, though, you would pass the horizon and continue inward, unaware of the freezing illusion. Two truths exist simultaneously. One where you remain on the edge, another where you vanish inside. Now imagine this applied to information. To the outside universe, perhaps your information remains smeared on the horizon. To you, it continues to fall inward. Which reality is true? Both? Neither? The paradox forces us to ask whether reality itself is consistent, or if truth fractures depending on perspective. The stakes are not limited to black holes alone. If information can truly vanish, then the past itself becomes unreliable. Every law of physics assumes that if we know the present state, we can trace back the chain of cause and effect to reconstruct the past. If information is lost, that link is broken. Imagine reading a book where chapters suddenly vanish, leaving you unable to know what happened before. The story of the universe would become fragmented, irretrievable. And yet, quantum mechanics insists this cannot happen. The paradox is like a cosmic trial, with relativity and quantum mechanics standing as witnesses, each swearing the other is wrong, while the universe itself refuses to reveal the verdict. Some modern thinkers believe that the resolution lies in a deeper theory, quantum gravity, a framework that unites relativity and quantum mechanics. Perhaps black holes do not destroy information, but transform it in ways our current physics cannot yet describe. Perhaps spacetime itself, the very arena in which these dramas unfold, is not fundamental but emergent, arising from something deeper, more abstract, something like information itself. If that is true, then the paradox is not a flaw in the universe but a clue, a crack in the cosmic shell, revealing a deeper order beneath. The black hole, far from being a graveyard of reality, might be a teacher, forcing us to confront the limits of knowledge. The black hole information paradox is not merely an academic puzzle. It is a reminder of how fragile our grasp on reality truly is. Two of the greatest triumphs of human thought, Einstein's relativity and the strange world of quantum mechanics, collide at the edge of these cosmic abysses, leaving us uncertain which way to turn. It is as if the universe has written a riddle at the threshold of existence, daring us to solve it. And perhaps, in that paradox, lies the very key to understanding not just black holes, but the fundamental nature of reality itself. When matter disappears into a black hole, does the universe forget? Or does it remember in a language we have yet to learn? The answer may define the ultimate story of existence. Cosmic Horizon Trap. Out at the very edge of the observable cosmos, a strange and haunting truth unfolds, a truth so subtle yet so absolute that it reshapes how we think about existence itself. The universe is not static, it is not silent, it is expanding. Every second, the very fabric of space stretches, pulling galaxies farther apart. At first, this seems like nothing more than celestial drift, like boats slowly moving away on a cosmic sea. But the farther out we look, the faster those boats sail. And at some ultimate distance, something terrifying happens. They cross the boundary of light itself. They recede not just quickly, but faster than light can ever chase them. Beyond that invisible wall, they vanish, not because they cease to exist, but because the universe itself ensures we will never see them again. This is the Cosmic Horizon Trap, a paradox that tells us, if something exists but cannot be observed, can it still be said to belong to our universe? Imagine standing on a shoreline and watching ships sail away. At first, you can see their masts, their sails, their outlines against the horizon. But as they move farther, the Earth's curvature swallows them. They are still out there, but for you, they may as well have disappeared. That's the ocean's horizon. The cosmic horizon works in a similar way, but far stranger. Because here, the ocean is space itself, and the curve that swallows galaxies is not a surface, but the speed of light itself. When galaxies cross that threshold, they don't simply shrink into the distance, they fall out of reality as far as we are concerned. Their light, no matter how fast it travels, can never outrun the expansion of the universe to reach us. They are not gone, but they are gone to us. Now consider what this means. When we look at the night sky, we are not just seeing stars. We are staring back in time. The light of Andromeda takes over 2 million years to reach us, meaning we see it not as it is, but as it was when humanity itself had not yet walked the earth. Push that further. The most distant galaxies we observe, through the eyes of telescopes like Hubble or James Webb, are seen as they were billions of years ago. In fact, the oldest light we can see is the cosmic microwave background, the faint afterglow of the Big Bang itself, frozen on our sky like an ancient fossil. Beyond that, no light survives. And yet, the universe continues infinitely outward. Entire realms of galaxies have already slipped behind the cosmic curtain. We know they must be there, because physics demands it. But for us, they are exiled beyond reach forever. They could burn, collide, collapse into black holes, or give birth to new civilizations, but from our perspective, their stories are locked in silence. Here lies the paradox. If those galaxies will never influence us, never send a photon, never deliver a single signal that can reach our detectors, then do they truly belong to the same universe? Or is the universe we live in nothing more than the observable bubble, a finite sphere carved by the speed of light? Think of a prisoner locked inside a room. The world beyond the walls may exist, but for the prisoner, reality shrinks to the chamber. The cosmic horizon is like those walls, except no force can break them. Even if we wait 1 trillion years, no key will unlock the galaxies that are drifting away faster than light. They are already sealed in their own destinies, and our sky is fated to forget them. The implications stretch into philosophy as much as physics. Our universe, vast and magnificent, might in truth be a fractal of isolation. Each observer in space has their own horizon, their own boundary of what can ever be known. For an alien civilization billions of light-years away, their night sky would be filled with galaxies we can never see, just as ours is filled with wonders they will never glimpse. The cosmos is not one shared canvas, but countless overlapping perspectives, each one a private painting of existence, bounded by the relentless speed of light. What you call the universe is not the whole, but only the part granted to you. Take this even further. The cosmic horizon trap means that with time, Even the galaxies we now see will be stolen from our sky. The universe's expansion is accelerating, driven by something we call dark energy, an unseen pressure that pushes everything apart. Today, we can still see billions of galaxies. But give the universe another 100 billion years, and nearly all of them will have vanished beyond the horizon. The night sky will grow emptier, lonelier, until only the stars of our local group remain. Future astronomers, if any life survives that far, will gaze at the heavens and see only silence. They will not even know that the great universe beyond their tiny island ever existed. For them, cosmology itself will be impossible. The evidence will have been erased by time. So again the question returns with heavier weight. What is real? Is reality only what we can measure, what can enter our telescopes, our equations, our minds? Or do we grant existence to the infinite unseen, the galaxies forever lost, the civilizations that may live and die beyond the horizon? This is not just science, it is philosophy pressed into the shape of physics. For if we insist that the universe is only what we can observe, then the true cosmos is dying piece by piece, trimmed down by expansion until it withers into a tiny island. But if we accept that reality extends beyond the horizon, then we must live with the haunting fact that most of it will remain a mystery forever. A reality that exists but cannot be proven. A truth that is there, but inaccessible. A universe that both belongs to us and does not. Consider also the human heart in this equation. Our longing to explore, to discover, is boundless. We send telescopes to peer at the edges of time, probes to crawl into the deep black of interstellar space. But here, the cosmic horizon stands as an ultimate wall. Not a wall of distance, but a wall of time itself. It reminds us of our limits, it humbles us. We may reach Mars, we may sail to other stars in distant futures, but we will never see the full tapestry of creation. There will always be parts of the universe that fall silent, that leave us behind. We are creatures forever locked inside a shrinking circle of light. And yet, maybe that is not despair, but beauty. For within this fragile horizon, existence blooms. Within this cosmic prison, life learned to think, to wonder, to ask questions about the infinite. The galaxies beyond may never speak to us, but their silence still teaches us something profound, that the universe is larger than imagination, deeper than reason, stranger than any dream. That truth itself is not something you own, but something you chase, knowing you will never catch it fully. The cosmic horizon trap is not just a boundary of physics, it is a mirror of our condition. To live is to exist inside limits, to yearn beyond them, and to find meaning not in what you can seize, but in what forever escapes you. Even as galaxies drift away faster than light, they remain part of a reality that once touched ours. Their photons may never arrive, but their existence still whispers through equations, through the relic glow of the Big Bang, through the very structure of space that shapes our fate. They are gone, yet their absence is presence. They are beyond us, yet they remind us that the universe is not ours to own. It is only ours to glimpse, for a moment, before the curtain of expansion draws shut. And so, when you look at the night sky, remember, what you see is not the whole, but only the fraction the cosmos allows you. Every star, every galaxy, is a survivor of that horizon, still within reach, still able to cast its light across the ocean of time. And beyond them lies the infinite silence, the unseeable, unknowable, unreachable, still real, still existing, though forever outside our grasp. The universe is larger than our vision, larger than our understanding. And perhaps that is the point. That in chasing the infinite, we learn not to capture it, but to be humbled by it. To stand on the shore of light, staring at the ships that sail beyond sight, and to realize that their vanishing is not loss, but a reminder of just how vast, how unfathomable reality truly is. Big Bang Singularity Paradox. In the beginning, before galaxies spun, before stars flared into light, before even the concept of time itself, there was a singularity. A point not larger than the head of a pin, yet containing everything, every atom, every galaxy, every law of nature, compressed into an inconceivable state of density. This is the paradox of the Big Bang. Physics tells us that singularities are where the rules collapse, where mathematics shatters into contradictions, where infinity itself sneaks into equations. But infinity, as powerful and majestic as it sounds, is not supposed to exist in physics. You cannot have infinite temperature, infinite density, infinite curvature of space. These are not real, measurable states of existence, but rather the signs that our theories have reached a breaking point. And yet, here we stand, told that the very birth of the universe began with exactly that, an impossibility. Imagine you are holding a balloon in your hand. Deflate it until there is almost nothing left. The air is squeezed out, but there is still space, still volume. Now imagine shrinking not just the air, not just matter, but the very fabric of space itself. Squeeze galaxies, stars, planets, atoms, protons, quarks, compress them past comprehension, until you arrive at a point of zero size and infinite density. That is what the equations of general relativity predict when we roll the cosmic clock backward to the very first instant. But here's the contradiction. Physics breaks when infinities appear. They are like red warning lights, telling us that we've taken the mathematics beyond its domain of truth. So, if the Big Bang begins with a singularity, does that mean our understanding of the universe starts with a lie? Or does it mean we have stumbled upon a truth so foreign, so alien, that even our most advanced theories cannot yet touch it? To feel the depth of this paradox, let's consider time. Time itself, as Einstein's relativity shows, is inseparable from space. They are a single woven fabric, space-time. Roll time back and the fabric contracts, folds, shrinks. At the singularity, time itself ceases to exist. There is no before, no earlier, no state of waiting for the Big Bang to arrive. That means the question, what happened before the universe began, is itself nonsensical, like asking what's north of the North Pole. And yet our minds rebel against this. We crave a cause, a trigger, a hand that lit the cosmic fuse. But what if the very structure of reality denies us this comfort, locking the origin in a cage of impossibility? Physicists have wrestled with this singularity paradox for decades. Stephen Hawking and Roger Penrose demonstrated mathematically that under the laws of relativity, singularities are unavoidable. But this is also the very point where relativity is no longer trustworthy. When density soars past the Planck scale, quantum mechanics must enter the scene, and here the two titans of modern science, relativity and quantum theory, refuse to cooperate. It is as though the universe is hiding its birth behind a curtain, and each time we try to peek, the curtain thickens with infinities. We are left asking, did the Big Bang truly begin from an infinite singularity, or is the singularity merely the shadow cast by an incomplete theory? Examples in physics show us why infinities cannot be real. Imagine dividing 1 by smaller and smaller numbers. 1 divided by 1 gives you 1. 1 divided by 1,000th gives you 1,000. Divide by 1 trillionth and you soar to a trillion. Keep dividing and you never stop rising, reaching infinity. But does infinity exist in the physical world? No. It is a mathematical illusion, useful in equations but never observed in reality. The heat of a fire can rise, but not to infinity. The density of a neutron star can crush atoms, but not infinitely. Even black holes, which represent singularities in relativity, may have their infinities cancelled by the rules of quantum gravity. So why should we believe that the universe itself began in a state of impossible infinity? Some theories suggest alternatives. Perhaps the singularity never truly existed. Perhaps the Big Bang was not the birth of all things, but a transition. Some propose a big bounce, where a previous universe collapsed and rebounded, like a cosmic heartbeat pulsing eternally. Others suggest that quantum fluctuations blurred the singularity into a finite, dense state, still unimaginable, but not infinite. String theory, loop quantum gravity, and other speculative frameworks each try to erase the singularity, replacing impossibility with something tangible. Yet none are proven, and the paradox remains like a scar at the edge of knowledge. Think of it like this. Imagine tracing the story of a person's life. You write down their childhood, their youth, their adulthood, every detail unfolding with clarity. But when you reach the moment of their birth, the paper turns blank. You cannot write what came before. The singularity is that blank page in the book of the cosmos. Every galaxy, every planet, every life is a chapter written after it, but the very first word, the first ink on the first page, remains hidden. This paradox is not just a mathematical puzzle. It is existential. If the universe was born from impossibility, what does that mean for everything we know? It means reality itself might rest upon something that cannot exist within the very laws it gave rise to. It is like a building standing on air, like music composed from silence. The fact that anything exists at all is already a miracle, but the singularity deepens the mystery into something almost unbearable. We want to know what happened, but the more we ask, the more the answers dissolve into infinity. And yet, this impossibility gave birth to everything: the stars that ignite the night, the atoms that form your body, the consciousness that now ponders its own origin. From a point that should not exist, existence itself erupted. The singularity paradox is a reminder that reality may be larger than logic, that perhaps impossibility is not a dead end but a doorway. If the cosmos could be born from infinity, then perhaps infinity is not a mistake, but the very key to creation. So, when you look up at the sky tonight, remember this: every glimmer of starlight, every breath you take, every thought in your mind, all of it flows from a paradox that should never have happened. And yet, here you are. The impossible happened, and it became the universe. Multiverse measure problem. Imagine tossing a coin. In your world, it lands heads. In another, it lands tails. In yet another, the coin never leaves your hand, or the laws of physics warp so that it hovers in midair forever. If the multiverse truly exists, infinite universes where every possible outcome is realized, then nothing is impossible. Every chance, no matter how small, is actualized somewhere. But here is where the paradox begins. If everything happens, how do we speak of probability at all? What does it mean to say an event is likely or rare, when somewhere it always occurs? This is the multiverse measure problem. In ordinary life, probability is straightforward. Roll a fair die, and you have a 1 in 6 chance of landing a 4. But in an infinite multiverse, every roll lands on 4 somewhere. In fact, every roll lands on all 6 numbers, and not just once, but endlessly. So why should we ever say 1 in 6? The phrase loses meaning if all outcomes exist equally. Yet our lives are guided by probabilities, by risks, odds, and likelihoods. Without them, prediction dissolves. If all outcomes are realized, how do we assign weight to them? This is not just philosophy, it's a crisis in modern cosmology. Theories of eternal inflation suggest that new universes constantly bubble into existence, each with its own laws of physics. Some may look like ours, others alien and unrecognizable. If infinitely many exist, then every possible history unfolds within them. Some contain worlds like ours, down to the finest detail of your heartbeat right now. Others diverge wildly. But if there are infinitely many, how do we count them? How do we say one outcome is more common than another? Infinity cannot be tallied like apples. Without a measure, probability becomes slippery. Consider a lottery. In our universe, the odds of winning might be 1 in 100 million. But in a multiverse, every ticket number is drawn somewhere. You both lose and win, across universes, both happen infinitely often. So what does probability mean? You might say, probability tells you what outcome to expect in your branch. But what gives your branch more weight than another? This is where the measure problem cuts deepest. If infinities exist, Not all infinities are equal. Some outcomes must be larger sets than others. But defining this measure is a mathematical nightmare. Here's an analogy. Imagine standing before an infinite library. Every book that can be written is on the shelves. Some shelves contain endless copies of the same book, others contain books written with a single letter difference. If you reach out randomly, how do you know which type of book you're more likely to grab? Without a system of measure, your choice is undefined. Infinity alone gives no preference. The multiverse is that library, and we are readers trapped within it, unsure how to weigh one story against another. This has consequences for science itself. Predictions in cosmology depend on probability. For example, why do we observe a universe with the physical constants we see? If all constants exist in some universe, then our observation alone doesn't explain anything. To explain why this set of constants appears probable, we must define a measure across universes. Some physicists suggest weighting universes by their volume, or by their ability to host observers. Others argue for more exotic rules. Yet each approach runs into paradoxes, infinities stacked against infinities, leading to contradictions. For instance, if you weight universes by size, inflationary universes that expand without bound dominate. But then smaller universes like ours seem almost impossible. If you weight by observers, you enter another paradox. What counts as an observer? Does every conscious being, every thought, every moment require its own measure? Suddenly, probability looks less like mathematics and more like metaphysics. The multiverse measure problem even affects personal meaning. If every choice you make is realized in some branch, does probability matter for you at all? When you take a risk, are you deciding, or merely splitting into versions that cover all possible outcomes? In one universe, you succeed. In another, you fail. In yet another, the choice itself is irrelevant because the world collapses before it matters. For you, the sense of probability still feels real, because you experience only one path. But if infinite versions of you walk all paths, then probability is not about what happens, but about how much of you experiences it. That, too, requires a measure, a way to say which branches carry more of your identity, more of your weight. This leaves us in a paradoxical state. Probability cannot be erased. We rely on it in science, in life, in thought. Yet in an infinite multiverse, probability cannot be defined in any simple way. It drowns in infinity. Until we solve the measure problem, our predictions about the cosmos remain unstable, like a compass spinning in every direction at once. And so we are left with a haunting question. If every outcome is guaranteed, what does it mean to call one outcome more likely? Are we navigating a universe of chance, or a multiverse of inevitabilities where chance is only the illusion of a single viewpoint? The measure problem reminds us of the fragility of our understanding. We speak of odds and risks, but in infinity, even language falters. Probability may not be a law of nature at all, just a shadow cast by limited perspective, fading as we stare into the endless corridors of the multiverse. Dark matter illusion. Imagine looking into the night sky and realizing that everything you see, the stars, the planets, the galaxies, even the atoms that make up your body, accounts for less than 5% of the universe. The rest, scientists tell us, is made of something invisible, undetectable, and almost ghostly. They call it dark matter, a hidden presence revealed not by sight but by the subtle tug of gravity. Galaxies spin too fast for their visible stars to hold together, yet they do not fly apart. Clusters of galaxies bend light in ways that luminous matter alone cannot explain. The invisible scaffolding of the cosmos is inferred, not seen. But here lies the disturbing possibility. What if this invisible matter does not exist at all? What if the flaw is not in the sky, but in our understanding of the law of gravity itself? For decades, physicists have treated dark matter as a placeholder, an unseen hand balancing the equations of the universe. And yet, Despite half a century of searching, no direct detection has ever succeeded. We build detectors buried deep underground, shielded from cosmic rays, waiting for the faintest whisper of a particle passing through, but silence greets us every time. We construct particle colliders, smashing atoms at unimaginable energies, hoping to glimpse evidence of dark matter in the debris, but nothing conclusive emerges. The mystery deepens. The question grows sharper. Are we chasing ghosts, or are we misunderstanding the very fabric of how gravity works? Consider the analogy of ancient astronomy. For centuries, people believed Earth was the unmoving center of the universe. When planets wandered in strange loops across the sky, astronomers invented epicycles, imaginary circles upon circles, to patch the model. The system became more complex, but the underlying assumption was wrong. When Copernicus and Kepler shifted the perspective to a sun-centered system, the loops vanished. Perhaps dark matter is our modern epicycle, a patch to preserve a flawed understanding of cosmic law. Maybe the problem is not missing matter, but missing comprehension of how space and gravity truly operate. Some theories, such as modified Newtonian dynamics, suggest that our equations of gravity break down at galactic scales. Instead of adding invisible matter, they propose altering the rules. In these models, the universe behaves differently in the vast reaches of intergalactic space than it does on Earth or in the solar system. Gravity may not be a single universal law but a layered phenomenon, changing with distance or scale. If that is true, then dark matter could be nothing more than the illusion created by our insistence on applying familiar rules too far. But if dark matter is real, its implications are staggering. It would mean the visible universe is just the foam on top of an unseen ocean, galaxies like scattered leaves floating on a sea of shadow. It would mean the true architecture of the cosmos is hidden, with filaments of invisible matter stretching across billions of light-years, shaping everything yet never shining, never touching light. Entirely new particles would exist, beyond the standard model of physics, hinting at realities we have never imagined. In that case, our ignorance is not a mistake but a doorway, proof that reality is stranger and richer than our senses or equations suggest. The dilemma sharpens when we confront the paradox of inference. To infer something is to admit we cannot see it directly. But inference can either reveal truth or conceal error. When you hear footsteps in the dark, you may infer a person, or you may be misled by the wind against the floorboards. The universe's footsteps echo in the form of gravitational curves, bending light, spinning galaxies, pulling clusters together. We infer dark matter. But perhaps it is only the wind of misunderstood gravity, whispering through the cosmic floorboards. What does this mean for us? It reveals that certainty is fragile, even in science. We imagine the universe as knowable, measurable, tamed by mathematics. Yet every equation rests on assumptions, and every observation can be interpreted through multiple lenses. Dark matter is either the greatest unseen presence in the universe or one of the greatest misinterpretations in human history. Either way, it forces humility. We are children drawing maps of an ocean while standing on the shore, unsure whether the waves conceal islands or trick us into chasing mirages. And perhaps that is the beauty of the dark matter illusion. It forces us to confront the limits of perception and theory alike. If dark matter exists, then reality is vastly deeper than we imagined, with hidden layers that sculpt our every star. If it does not, then our laws themselves must be rewritten, reshaped, reimagined, like Copernicus redrawing the sky. Either way, the illusion reveals truth, not by giving answers, but by showing us how fragile our answers are. The universe, it seems, is not a solved puzzle, but a riddle that reshapes itself the moment we think we understand. In the end, dark matter may be real, or it may be illusion. But in either case, it teaches us that the cosmos is not transparent, not obvious, not obedient to our expectations. It is a theater of shadows where every light conceals more darkness. And in chasing that darkness, whether ghost or law, we glimpse the humbling fact that we are not masters of the universe, but seekers, stumbling in awe, guided not by certainty but by wonder. Quantum vacuum puzzle. Picture yourself staring into what appears to be absolute emptiness. A void, a stretch of nothing, silent and still. For centuries, philosophers and scientists alike imagined such emptiness as the purest baseline of reality, a blank canvas on which existence is painted. But modern physics reveals something stranger, something that twists our very notion of nothingness. The vacuum, the so-called emptiness of space, is not truly empty at all. Instead, it teems with invisible activity, virtual particles that appear and vanish in fleeting bursts, quantum whispers echoing in silence. This is the quantum vacuum puzzle, a paradox that shows that even nothingness refuses to be nothing, that the void itself is restless and alive. To understand the depth of this puzzle, imagine placing a box in deep, intergalactic space, far from stars, galaxies, and radiation. Seal it perfectly. Common sense tells us that inside there should be nothing, a complete and perfect emptiness. But quantum mechanics says otherwise. Within that box, particles of energy will flicker into being, live for a blink of time, and then disappear. They are called virtual particles, not because they are imaginary, but because they cannot be directly measured, only inferred through their effects. They pop into existence in pairs, a particle and an antiparticle, born out of the fabric of the vacuum itself, only to annihilate back into nothingness. This dance happens everywhere, all the time, even in what we call empty space. Nothingness, it turns out, is an illusion. This strange activity is not just speculation. We see its fingerprints in phenomena like the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a mysterious force pulling them together. No external field drives this. Instead, it is the quantum vacuum itself, the fluctuations of invisible particles pushing and pulling from the void. In a sense, the plates feel the pressure of nothingness. Here, the universe reveals that absence is itself a form of presence, and silence still hums with unseen sound. The paradox deepens when we consider the implications. If empty space seethes with particles, then it is not truly empty. It holds an energy, called vacuum energy, woven into the very structure of reality. And yet, when physicists try to calculate how much energy the quantum vacuum contains, the results spiral into absurdity. The equations predict an energy density so large that, if true, the universe would instantly collapse under its own weight. But clearly, it does not. Instead, the cosmos expands calmly, governed by a mysterious balance we cannot yet decipher. The contradiction is staggering. Theory predicts a storm. Observation shows calm. Reality lives between two irreconcilable truths, echoing the same paradox that drives the deepest mysteries of physics. Consider also the link between this puzzle and the expansion of the universe. Cosmologists observe that space itself is stretching, galaxies drifting apart as if pushed by some hidden force. This acceleration is attributed to what we call dark energy, a term as mysterious as the phenomenon it describes. Many suspect that dark energy is nothing more than the energy of the vacuum itself, the restless sea of virtual particles pushing outward on the fabric of space. If this is true, then nothingness is not just a passive stage but an active player in the cosmic drama, dictating the fate of galaxies and the shape of eternity. The void itself writes the script of the universe. To grasp the strangeness, imagine trying to define what nothing means. True emptiness should mean no particles, no fields, no energy, no space, not even time. But the quantum vacuum refuses this definition. Space without matter still contains energy. Silence still vibrates. Stillness still moves. The universe seems to forbid absolute nothingness, as though creation requires contradiction at its foundation. Perhaps this is the ultimate irony, that reality itself cannot exist without paradox, and even non-existence hides the seeds of existence. Examples of this contradiction appear everywhere in physics. Virtual particles near the edge of black holes, for instance, are believed to be the source of Hawking radiation, the faint whisper of energy that allows black holes to evaporate over unimaginable timescales. In this picture, the vacuum is not just a background but a source of cosmic change, giving rise to radiation, motion, and even the evaporation of the universe's darkest objects. Once again, what appears empty is filled with infinite potential. The quantum vacuum puzzle does more than challenge our understanding of physics. It also presses against the boundaries of philosophy. If nothingness cannot exist without something, then perhaps the very idea of absolute emptiness is meaningless. Maybe there is no nothing. Maybe the universe itself emerged not from a void but from a vacuum already buzzing with possibility. What we call the beginning, the Big Bang, might not have been the birth of something from nothing, but a transformation of one kind of something into another. This thought collapses the divide between being and non-being, between silence and sound, between zero and infinity. The paradox remains unsolved. We do not yet know why the vacuum behaves as it does, why calculations explode into impossibility, or why the universe balances on a razor's edge between emptiness and energy. But perhaps that is the point. The quantum vacuum puzzle is not a flaw in our reasoning, but a signpost pointing toward deeper truths. It tells us that the universe hides its secrets not in abundance, but in apparent absence. That to look into nothing is to see the outline of everything. That silence, when listened to closely enough, sings. So when you gaze into the night sky, into the dark spaces between stars, remember this: you are not looking into emptiness. You are looking into a sea of invisible creation, where particles rise and fall like waves too quick for the eye to catch. The vacuum is alive, restless, and inescapable. Nothingness itself is the greatest contradiction, and through it, the universe whispers its most profound secret, that even emptiness is full. Time-symmetry paradox. Time is a river we all drift upon, yet the direction of its flow is one of the deepest mysteries in all of existence. Physics tells us something unnerving. The fundamental laws that govern the universe, whether the motion of planets, the dance of particles, or the structure of atoms, do not care about direction. They work the same way forward in time as they do backward. Reverse the film of two colliding billiard balls, and the mathematics still holds perfectly. Quantum mechanics, relativity, Newton's laws, all indifferent to which way the clock ticks. This symmetry is elegant, consistent, almost divine in its balance. And yet, when we look at our own lives, at memory, at decay, at history itself, we find something brutally one-sided. We are born, we age, we die. We remember the past, but never the future. The coffee cools, the glass shatters, the star burns out. Never once does time flow in reverse. The arrow of time pierces us in only one direction. Why? Consider the paradox. If the universe's laws do not distinguish between forward and backward, why does reality itself feel so trapped in a single flow? One answer lies in entropy, the measure of disorder. At every step, the universe moves from order toward chaos. Eggs crack but never uncrack, smoke disperses but never reassembles, heat flows from hot to cold but never the other way around. Entropy increases, and in that increase, we humans find the arrow of time. Our perception of forward is tethered to the universe's unstoppable slide into greater disorder. But even this raises a deeper question. Why did the universe begin in such an extraordinarily ordered state, so low in entropy, that it allowed time to even have this direction at all? Imagine shuffling a deck of cards. The more you shuffle, the more random it becomes, until no arrangement seems special. Yet if you stumbled upon a deck ordered perfectly from ace to king, you'd recognize its strangeness instantly. The early universe was like that deck, astonishingly ordered, balanced, smooth. And from that improbable starting point, it has been unraveling ever since. Galaxies formed, stars ignited, planets cooled, life emerged, and we, creatures of memory and anticipation, became aware of the unraveling. Our sense of past and future may simply be the echo of that original order unwinding. But there is something profoundly disturbing in this. If time's arrow is merely a reflection of entropy, then on the most fundamental level, there is no real difference between the past and the future. Every particle of matter, every photon of light, follows laws that would work just as well in reverse. In theory, you could imagine an entire universe where time flows backward, where the dead rise from graves, where ashes form themselves into logs, where memories run from tomorrow to yesterday. Nothing in the math forbids it. And yet, such a universe feels impossible to us, alien to every fiber of human experience. Why should existence itself be indifferent, while consciousness is not? Think of memory. Why do we remember yesterday but not tomorrow? If the laws of physics are symmetric, why is the mind asymmetric? Some scientists suggest that memory itself is a product of entropy. The brain records the past because the past was lower in entropy and information could be etched into it. The future, being undefined and higher in entropy, cannot yet be written. Others argue that consciousness itself generates the illusion of time's arrow, that we, as biological machines, experience the one-way flow because we are built upon processes that burn energy, dissipate heat, and increase disorder. To live is to ride entropy's current, and so we only ever drift downstream. And yet, physics continues to mock us with symmetry. Take the equations of antimatter, mirror particles of our universe. Reverse time, and they behave as if they are matter moving forward. In a way, parts of the universe are already living out reverse timelines, invisible to our own arrow. The symmetry is not broken, it only hides itself behind the veil of our perception. Some even propose that our universe began in not one, but two directions. That the Big Bang may have spawned twin arrows of time, two universes expanding outward, each flowing away from the singular origin, one forward, one backward, neither privileged, each the mirror of the other. If true, then what we call the past may simply be another civilization's future, forever inaccessible across the gulf of reversed arrows. This paradox doesn't stop at physics, it cuts into philosophy. If time can run both ways, then is causality itself an illusion? When you drop a glass and it shatters, do you believe the shattering is caused by the fall? Or is the fall caused by the shattering in reverse time? The laws of motion would accept either interpretation. What we call cause and effect may be nothing more than a story told by beings trapped inside a single direction. Perhaps in the grand design of reality, there is no past pushing into the future, no future pulled from the past, only a timeless whole, complete and symmetric, with us crawling along one thread and calling it destiny. But then, why do we feel the weight of time so deeply? Why does memory sting? Why does hope burn? Why does loss crush us in only one direction? The paradox becomes more than scientific, it becomes personal. The symmetry of time tells us the universe does not care about forward or backward. But our hearts do. We ache because the arrow points one way, because moments pass and never return, because tomorrow never becomes yesterday again. Time symmetry whispers a terrifying truth, that the arrow is not written into the fabric of reality, it may only be written into us. So when you stare at an old photograph, when you replay a memory of childhood, when you grieve for what is gone, remember that physics itself does not forbid those moments from existing still. They are not destroyed, they are simply placed in another frame of the grand film, waiting on the reel. The universe does not lose them, it only refuses to let us walk back to them. The arrow holds us prisoner, not the laws. Somewhere in the symmetry of time, past and future coexist, balanced perfectly, like two mirrors facing each other in infinite reflection. We move through one reflection and call it reality, but the other stands there, unreachable, reminding us that existence is far stranger than the arrow allows us to believe. This is the time symmetry paradox. Laws that honor both directions, life that knows only one. A cosmos that is reversible, inhabited by beings who are not. And perhaps that tension, that crack between physics and perception, is the true definition of time itself. Cosmic fine-tuning dilemma. From the moment we open our eyes to the night sky, one thing becomes clear. The universe is not random chaos. It is balanced, delicate, astonishingly precise. The very fabric of existence is stitched together by numbers so exact, so narrowly defined, that even the smallest change would have made life impossible. This is the dilemma of cosmic fine-tuning. The universe seems engineered for life, yet engineering implies an engineer. Tuning suggests a tuner. And so we are left caught between two possibilities. Is it all mere chance, a cosmic lottery win beyond imagination, or does intelligence, purpose, perhaps even design, stand behind existence itself? Let us begin with the numbers. The strength of gravity, the ratio of the electron to the proton, the speed of light, the expansion rate of the universe, all these constants rest on razor-thin margins. If gravity were slightly stronger, the universe would have collapsed back on itself before stars could form. If it were slightly weaker, matter would never have clumped together at all. No galaxies, no suns, no planets. If the strong nuclear force that binds protons and neutrons inside the atom had been weaker by just a fraction, atomic nuclei would never have formed, and chemistry, as we know it, would vanish. If it had been stronger, stars would have burned through their fuel too quickly, snuffing out before life had time to evolve. Even the cosmological constant, which governs the acceleration of the universe's expansion, is so finely balanced that Steven Weinberg called its value extraordinarily improbable. Had it been even a hair off, the cosmos would have torn itself apart or frozen into lifeless stillness. What we are faced with is not a universe that is merely habitable. It is a universe balanced on a knife's edge. Imagine rolling dice not once, not twice, but trillions upon trillions of times, and every time, against all odds, the dice land perfectly. That is what the fine-tuning problem suggests. Life exists only because the numbers aligned in an almost impossibly exact way. This is not philosophy alone. It is cold, precise physics whispering to us that something very strange lies at the root of reality. But if the universe is fine-tuned, who or what did the tuning? One possibility is chance, pure, blind, merciless chance. Perhaps the laws of physics simply turned out this way, with no deeper explanation, and against all odds, we find ourselves here. This is the brute fact hypothesis. The universe is the way it is, end of story. Yet our minds struggle with this. It feels unsatisfying, like being told a masterpiece painting just spilled itself out of a bucket of paint. Possible, maybe, but unlikely. Another possibility is the multiverse. Imagine not one universe, but countless universes, each with different laws, constants, and conditions. In most of them, there is nothing but void, chaos, or collapse. But in one, just one, the numbers align, and we happen to live inside it. In this view, our existence is not miraculous, but inevitable. If enough universes exist, one must eventually produce life. The multiverse is appealing because it explains fine-tuning without requiring intelligence, but it is also deeply unsatisfying, because these other universes may forever remain unobservable. It shifts the mystery sideways, without truly solving it. And then there is the possibility that the universe is tuned because intelligence lies at its foundation. That life itself is not an accident but the very reason the cosmos exists. Some scientists, like Freeman Dyson, suggested that the universe, in some strange sense, knew we were coming. The anthropic principle goes further, claiming that the laws must allow life, because otherwise there would be no one to ask the question. But beneath these ideas lurks a haunting thought. Is intelligence an emergent property of the cosmos, or is the cosmos itself the product of intelligence? Did consciousness arise out of the universe, or did the universe arise out of consciousness? The fine-tuning dilemma presses harder when we realize just how unlikely our presence is. Consider water. For life as we know it, water's properties are essential. But those properties depend on the precise strength of hydrogen bonds and the exact behavior of electrons. Tweak those forces slightly, and water would not be a liquid, but a gas or a solid across all temperatures. DNA could not form. Proteins could not fold. Life could not spark. Yet here we are, made of water, carrying within us the chemistry of stars. Some argue that asking who tuned the universe is itself a flawed question. Perhaps the cosmos is not tuned for life, but life adapted itself to the cosmos. We exist not because the universe was designed for us, but because we are the rare byproduct of conditions that happen to allow it. Just as a puddle fits perfectly into the hole it fills, we fit perfectly into the laws of the cosmos, not because they were designed for us, but because only under these laws could beings like us emerge to ask the question. But even then, the sheer improbability of those laws gnaws at reason. The dilemma deepens further when we add consciousness into the picture. If the universe is not only fine-tuned for matter and energy, but also for the rise of beings who can question their own existence, then perhaps fine-tuning is not just about survival, it is about awareness. About the cosmos folding back upon itself through us, staring into the mirror of its own origins. Is intelligence the tuner itself, reaching back through time to ensure its own possibility? Or is intelligence the illusion born from chance, clinging to meaning where none exists? The fine-tuning paradox forces us into a confrontation with the ultimate question: chance or design? Random lottery or cosmic intention? And the truth is, we do not yet know. But perhaps the deeper answer is that fine-tuning is not meant to be solved, only experienced. It is the awe we feel when we realize how fragile existence is, and yet how certain it feels. It is the wonder that in a universe hostile to life, against infinite odds, life still found a way. So, next time you look at the stars, remember this: every constant, every law, every delicate balance in the universe had to be just right, or you would not be here to wonder at all. The cosmos may be tuned by chance, or by mind, or by something beyond both. But either way, it leaves us with a truth that is as humbling as it is electrifying. Existence itself is the greatest mystery, and we are its witnesses. Cosmic inflation puzzle. Imagine looking up at the night sky. The stars scatter like glitter, the galaxies stretch endlessly, yet everywhere you look, no matter the direction, the cosmos appears astonishingly smooth. The same temperature, the same glow of the cosmic microwave background, uniform to 1 part in 100,000. This is strange. Because if the universe began in a chaotic explosion, as the Big Bang suggests, you would expect it to be messy, uneven, fractured. Some parts too hot, others too cold, light and matter jumbled like shattered glass. Instead, we see order, an elegant evenness that defies common sense. To solve this, physicists proposed inflation. Inflation theory says that in the first trillionth of a second, the universe expanded faster than the speed of light, swelling from subatomic size to cosmic scale in an instant. Like blowing up a balloon, inflation smoothed out the wrinkles, stretched out the irregularities, and left behind the uniform sky we see today. It solved the horizon problem. Why the cosmos looks the same everywhere, even in regions too far apart to have ever communicated. It also solved the flatness problem. Why the geometry of space seems so perfectly balanced, neither curving inward nor outward, but lying flat like an infinite sheet. Inflation looked like the master key to the universe's earliest riddles. But then comes the puzzle, the paradox hidden within the solution. Inflation itself requires improbable fine-tuning. For inflation to happen, the universe needed to be in an almost impossibly special state. The energy density of the vacuum had to be just right. The field driving inflation, the inflaton, had to sit perched on a plateau of its potential energy, smooth enough to roll slowly, steady enough not to collapse, precise enough to inflate space evenly. Too steep, and the universe collapses. Too shallow, and inflation never ends. Too lumpy, and we don't get the smooth cosmos we see. Out of countless possible beginnings, only an infinitesimal fraction would ever produce inflation. So in solving the mystery of cosmic uniformity, we introduce a deeper one. Why did inflation itself occur at all? Think of it like this. Imagine shuffling a deck of cards and dealing out 52 in a row. The odds of arranging them in perfect order, ace to king, all suits aligned, are astronomically small. Yet inflation requires a hand even rarer than that. The early universe had to be dealt not just a special arrangement, but the most delicately balanced hand possible, one that allowed a fleeting moment of runaway expansion. Why should the universe have been born in such an unlikely state? Inflation explains smoothness only by assuming an even greater initial improbability. Some physicists argue this is not a bug but a feature. Perhaps inflation is natural in quantum fields. Perhaps the multiverse births infinite universes, and only those with inflation give rise to observers like us. In this view, fine-tuning is explained by selection bias. We live in one of the rare universes where inflation occurred simply because universes without inflation could not harbor us. But this anthropic principle feels unsatisfying, more like a philosophical escape than a scientific solution. It pushes the question back. Why does the multiverse exist, and why does it allow inflation at all? Others propose alternatives. Maybe inflation is not the answer. Competing theories, like bouncing cosmologies or emergent universes, suggest that the cosmos may have gone through cycles of contraction and expansion, or may have always existed in some form. These models try to explain uniformity without requiring the improbable setup inflation demands. Yet none are proven. And so we stand in a paradox. The very theory that elegantly explains the smoothness of the cosmos is built upon the unlikely scaffolding of conditions it cannot explain. Here lies the heart of the cosmic inflation puzzle. Inflation makes the universe comprehensible, but only if we assume the incomprehensible. We replace one improbability, the uniformity of the cosmos, with another, the fine-tuning of inflation itself. It is like solving a riddle by inventing an answer more mysterious than the question. The solution and the problem collapse into one. And yet, perhaps this is the lesson. The universe may not owe us simplicity. It may not offer an easy chain of explanations where each link is neat and probable. Instead, it may whisper that reality itself is improbable, that existence always balances on a razor's edge. Inflation does not erase the mystery. It deepens it. It reminds us that the origin of everything, the very spark that stretched time and space, remains a puzzle shimmering just beyond our grasp. So when you gaze into the night sky, remember, the uniform calm you see across the stars is not the whole truth. Beneath that smoothness lies a secret, a paradox written into the fabric of beginnings. Inflation makes the universe possible, but only by demanding a cosmic miracle at the start. And until we understand why that miracle occurred, the first heartbeat of creation remains the most profound riddle of all. Observable universe boundary. Picture this. When you step outside on a clear night and look up at the sky, every star you see is part of just a tiny neighborhood in the galaxy, and even the galaxy itself is just a speck in the wider cosmos. Now imagine that all of human science, all of astronomy, all of cosmology, is based on a sphere we call the observable universe. This sphere is not the universe itself, it is only the portion from which light has had time to reach us since the birth of time. Beyond that, beyond the faint glow of the cosmic microwave background, beyond the most distant galaxies we can glimpse with our best telescopes, the universe may stretch on without end. Or it may curve back on itself. Or it may spawn regions so different from ours that our laws of physics don't even apply. And yet, we take this fragment, this visible slice, and treat it as though it were the whole. Science becomes at once the greatest act of vision and the most profound act of blindness. The paradox lies in the boundary itself. The speed of light is finite. The universe has an age, around 13.8 billion years. Multiply those two limits and you get a horizon, a cosmic event boundary we cannot see beyond. Not because there is nothing there, but because there has not been enough time for its light to arrive. It's like standing on the shore of an infinite ocean at night. You can see the waves lapping at your feet, the faint shimmer of the moonlit surface extending into darkness, but beyond that darkness may be more sea, or cliffs, or islands, or nothing at all. You don't know, because the light hasn't reached you. The observable universe is like that shoreline, defining what we can measure, but not what exists. This limitation shapes our science in ways that are almost impossible to notice because they are everywhere. For example, we assume the laws of physics are universal. That gravity works the same way in a galaxy 5 billion light-years away as it does in your kitchen when you drop a glass. But is that assumption safe? We do not know. We cannot experiment beyond our horizon. We trust symmetry, elegance, and consistency, but we are extrapolating from a very small sample, like trying to understand the whole ocean by studying a bucket of seawater. It may tell us a lot, but it does not guarantee that the same rules apply everywhere. Even the shape of the universe remains hidden. It may be flat, stretching endlessly in every direction. It may be curved like the surface of a sphere, finite but unbounded, looping back on itself so that if you traveled far enough you could eventually return to your starting point. Or it may be saddle-shaped, warped in ways we cannot intuit. All of these models fit within the sliver of reality we can observe. We are like ants crawling across a patch of floor, arguing about whether the entire building is flat, domed, or endless, unable to step outside to check. And then there is the question of what lies truly beyond. Some cosmologists suggest there are entire regions of the universe we will never see, not because of time limits, but because expansion itself is accelerating. Galaxies are rushing away faster than light can keep up, carried on the swelling fabric of space. These galaxies are not only invisible to us now, they will remain invisible forever. No future telescope, no future civilization, no matter how advanced, will ever glimpse them. They are, in a sense, erased from our cosmic story, though they still exist. This creates a strange tragedy. Most of the universe is already lost to us, not because it vanished, but because the universe is pulling it away faster than we can chase. Think of the implication for our understanding. Every scientific law, every cosmic principle, is drawn from a map where most of the territory has been permanently folded away. It's like trying to understand human history by studying only one village, one generation, one library of books. And yet, within that narrow boundary, we create vast theories. The Big Bang, dark matter, dark energy, all extrapolations from the observable sliver. Our science is therefore both enormous in its ambition and profoundly blind in its foundation. We see the grandest structures ever imagined, but we also admit that the majority of reality is invisible, unreachable, unknowable. To ground this paradox in a human example, imagine a blindfolded person standing in a room, able only to sense what lies within arm's reach. From touch alone, they could infer the existence of walls, furniture, perhaps the texture of the floor. But beyond their reach, beyond their blindfold, the room may extend further or end abruptly. They can make models, predictions, hypotheses, but their knowledge is bounded. The observable universe is our cosmic blindfold. We touch what is near, infer what is far, but the true extent of the room may be vastly different from what we imagine. Some philosophers take this further. They argue that the boundary of the observable universe is not just a scientific limit, but a conceptual one. That even if we could travel faster than light, even if we could live forever, our perspective would always be bound by horizons. Knowledge itself may always carry an edge, a line beyond which the unknown looms. To live in the universe is to live within a mystery that cannot be solved, only deepened. And yet, perhaps this is what makes the quest so compelling. The boundary does not diminish science, it defines it. The fact that we can see as far as we do, that we can measure the afterglow of creation itself in the cosmic microwave background, that we can map galaxies billions of light-years away, is already staggering. Our blindness is paired with vision. We are creatures on a shore, unable to cross the ocean, yet able to imagine its depths, to hear its waves, to chart its tides by moonlight. The unknown is not a failure of science, but its horizon. Beyond that horizon may be infinite universes, or nothing at all, or something stranger than both. In the end, the paradox of the observable universe boundary is this. We live inside a bubble of knowledge that feels complete, yet is only partial. Our science is vast, but it is also blind. We treat the part as the whole, and in doing so we both illuminate reality and conceal it. The cosmos laughs at our certainty, reminding us that beyond the faint glow of our horizon lies the greater part of truth, forever hidden, forever imagined, forever beyond. Boltzmann brain problem. Imagine, for a moment, that everything you know, your memories, your body, your history, even the earth beneath your feet, could be an illusion. Not in the sense of a dream or a simulation, but in a far stranger and colder way. Physics tells us that in an infinite universe governed by randomness and probability, there is always a chance, however small, that particles will randomly arrange themselves into complex structures. Given enough time, given infinite space, this chance becomes not just possible, but inevitable. Out of chaos, order can momentarily arise. And among the most extraordinary forms of order imaginable is a conscious brain. Not born through evolution, not raised in a body, but simply assembled by chance out of the swirling void. This is the Boltzmann brain problem, the unsettling possibility that you are not who you think you are, but instead a fleeting mind floating in chaos, conjured by randomness for only a moment before dissolving back into nothing. The idea originates with Ludwig Boltzmann, the 19th-century physicist who tried to explain why our universe seems to be so ordered, so low in entropy, when the natural tendency of everything is toward disorder. He imagined a universe that, on the grandest scales, is mostly chaos, high entropy, thermal equilibrium. Yet within this vast sea of disorder, tiny islands of order occasionally form by chance. These are fluctuations, temporary decreases in entropy that emerge simply because probability allows them. From this reasoning, one could imagine not just stars and galaxies forming from chaos, but even something as bizarre as a fully formed human brain, complete with false memories, false experiences, and the illusion of an entire past. It may last for only a heartbeat of time before disintegrating again, but in that instant, it would feel real. It would feel exactly like you. Here lies the terrifying question. How can you know you are not such a brain? If all your senses, all your memories, all your beliefs can be manufactured by a random fluctuation, what separates stable reality from temporary illusion? The paradox grows sharper when you consider numbers. If the universe is infinite and eternal, then it should produce far more Boltzmann brains than entire stable civilizations. After all, it is far less improbable for the universe to assemble a single functioning brain than it is to assemble billions of stars, planets, and the slow machinery of evolution. That means, statistically speaking, you are more likely to be a random, momentary consciousness than a genuine being living in a stable, continuous world. The logic is merciless. If probability rules all, then the ground beneath your feet may not exist at all. Imagine you are reading this sentence not as a human who has lived years of life, but as a consciousness that came into existence just seconds ago, already equipped with memories of childhood, family, language, and history. You feel continuity because those memories are part of the structure, not because they ever truly happened. When this fleeting arrangement of particles dissolves, your entire reality will vanish, leaving no trace that you ever existed. This is the nightmare edge of the Boltzmann brain problem, that existence itself may be a statistical mirage. Yet, physicists and philosophers push back against this. If our reality were dominated by Boltzmann brains, then science itself would collapse. Every observation, every experiment, every piece of evidence we trust could just be the random noise of a fabricated memory. The very laws of physics we use to predict the future could be nothing but illusions embedded in our temporary minds. But the fact that we do see order, that the universe around us appears consistent and predictable, suggests that perhaps we are not mere fluctuations. Some argue that any cosmological model which predicts that Boltzmann brains vastly outnumber ordinary observers must be rejected, because it cannot account for the stability and coherence we actually perceive. In this way, the Boltzmann brain paradox becomes not just a philosophical puzzle, but a filter for scientific theories. If a model leads to a universe swarming with illusory minds, then it must be wrong, or else reality itself is beyond reason. Still, the problem gnaws at the edges of thought, because probability never disappears. Given infinite time, infinite space, the appearance of Boltzmann brains is inevitable. The real question is not whether they exist, but how to ensure that they are rare, that our universe is not ruled by them. Some scientists turn to the concept of cosmic inflation, the rapid expansion of space after the Big Bang, as a way to explain why our universe is filled with coherent structures, galaxies, and life forms instead of random, disjointed minds. Others believe that future theories of quantum gravity may solve the paradox, showing that entropy fluctuations cannot produce stable consciousness in the way Boltzmann imagined. But as of now, the possibility remains, a quiet, haunting reminder that our existence may not be as grounded as we wish to believe. Think about this. You may be a genuine human being with a past and a future, part of a grand, evolving universe. Or you may be a statistical phantom, assembled for just this moment, with memories that never happened and a world that will vanish as soon as your consciousness fades. The paradox forces you to confront the fragility of identity, the uncertainty of reality, and the sheer strangeness of existence itself. Are you the product of billions of years of cosmic evolution, or just a spark in the darkness, flickering for an instant in a sea of chaos? The Boltzmann brain problem leaves the answer uncertain, and perhaps that uncertainty is the truest reflection of what it means to exist. Fermi paradox. The night sky is a cathedral of light. Stars blaze in their billions, galaxies spiral by the trillions, and planets circle in numbers beyond comprehension. In such immensity, life should not be rare, it should be inevitable. Our own existence proves that biology can arise from matter, that consciousness can awaken from chemistry. And if it happened here, why not there? Why not everywhere? Statistically, the universe should be teeming with civilizations. Some younger than us, some older by millions of years, perhaps so advanced that their technologies appear like magic. And yet, when we listen to the great silence of space, no voices answer. No signals crackle across the void. No ships streak across the sky. The stars remain mute, the cosmos empty. This is the Fermi paradox. If intelligent life is so probable, then where is everyone? Consider the numbers. In our galaxy alone, there are roughly 400 billion stars. Astronomers estimate that at least half host planets, many within habitable zones where liquid water could exist. That means billions of possible Earths scattered just in the Milky Way. Across the universe, the numbers rise to sextillions, planets enough for life to flourish 1 trillion times over. By pure probability, life should not only exist elsewhere, it should be common. Civilizations should rise, explore, colonize, and eventually leave evidence of their presence in the stars. But every time we aim our telescopes, every time we build new instruments to capture faint whispers of radio waves, we are met with silence. The silence is not absence. It is deafening, paradoxical, an echo that challenges our understanding of existence itself. One possibility is that we are early. That life is still awakening across the cosmos, and civilizations are rare sprouts in a universe that has only just begun to bloom. After all, stars will continue to form for trillions of years, long after humanity is gone. Perhaps we are among the first, not the latecomers. But if so, then the responsibility is staggering. We may not just be one of many. We may be the seed, the first voice to carry intelligence into the great quiet. Another explanation is darker. Perhaps civilizations emerge, but they do not last. They rise, as we have, and then collapse under their own weight, war, resource exhaustion, or the relentless grip of entropy. Some call this the Great Filter, an unseen barrier that most life cannot cross. The filter could lie behind us, in the improbability of life itself, or ahead of us, in challenges no species survives. If it lies ahead, then the silence of space is not mystery but warning. Every star that fails to speak becomes a tombstone in the galactic graveyard. There is another possibility. Life is out there, but it hides. Imagine a universe where intelligence learns quickly that survival means silence. Broadcasting your presence could invite predation from older, more ruthless civilizations. Just as tribes in ancient forests learn to move in shadows, galactic civilizations may cloak themselves, using technology invisible to our eyes. To us, the stars appear quiet. But perhaps it is only the quiet of a hunted forest, where countless beings hold their breath. And then there is the possibility that life is here, but we cannot recognize it. Advanced civilizations may use methods of communication beyond our comprehension, signals embedded in dimensions we cannot yet perceive, technologies indistinguishable from the fabric of reality itself. To ants crawling in the dirt, human highways are incomprehensible. To us, the works of an ancient galactic civilization might appear as nothing more than natural law. The silence, then, may not be silence at all, but our inability to listen in the right way. Some propose a final chilling answer, that we are alone. That despite the vastness, despite the probabilities, Earth is the singular cradle of consciousness in the entire observable universe. If true, then we are the rarest phenomenon in existence, lonely sparks of awareness in a sea of darkness. This idea is at once terrifying and beautiful. Terrifying, because it means no help is coming, no other voices will share the burden of existence. Beautiful, because it means we are the universe's only chance to know itself. Every thought, every poem, every discovery becomes sacred, a fragile miracle of awareness in an otherwise indifferent expanse. And yet, the paradox persists. Each night the stars shine as reminders that the question remains unanswered. Perhaps the silence is temporary. Perhaps one day a signal will arrive, faint but deliberate, carrying proof that we are not alone. Or perhaps the silence is eternal, the final truth of existence. Either way, the Fermi paradox forces us to confront our place in the cosmos. Are we one among many, or are we the only? Are we destined to join a galactic chorus, or doomed to sing alone forever? When Enrico Fermi asked the question, "Where is everyone?" he distilled into 4 words the greatest mystery of all time. The silence of the stars is not emptiness. It is a mirror, reflecting our fears, our hopes, and our fragility. It demands that we look inward as much as outward. For in the end, the Fermi paradox may not just be about others. It may be about us, about whether we survive long enough to send our own voice into the dark, and whether we choose to listen when the universe finally answers back. Anthropic principle loop. The anthropic principle begins with a curious truth. The universe seems perfectly suited for us. The constants of nature, gravity, electromagnetism, nuclear forces, the rate of expansion, all align with uncanny precision. If any were even slightly different, stars would not ignite, planets would not form, chemistry would fail, and life as we know it would never appear. And yet here we are, gazing into the cosmos and marveling at how astonishingly lucky we must be. To explain this, some invoke the anthropic principle, which in its simplest form states, "Of course the universe fits us, because if it didn't, we wouldn't be here to notice." At first, this feels clever. It transforms an impossible miracle into an inevitability. But look deeper, and you realize the anthropic principle circles back on itself. It explains everything by explaining nothing. It says, in effect, we exist because we exist. It feels like a conclusion, yet offers no true answer. This is the anthropic principle loop, a paradox disguised as an explanation, a mirror that reflects only itself. Imagine a lottery with odds so impossible that winning seems absurd. 1 person in 10 trillion. And yet someone does win. When asked how, the winner shrugs and says, "Well, if I hadn't won, I wouldn't be here to tell you." That is technically true, but it hides the deeper improbability that such a win occurred at all. Likewise, the anthropic principle tells us that we observe a universe compatible with life because only such a universe allows observers. But that is less an explanation and more a tautology. It soothes without solving. The problem sharpens when we consider alternatives. If the universe had been born with different constants, then no life, no mind, no witness would exist. There would be no one to ask the question. So perhaps our existence forces us into a narrow slice of possibility. But why does that slice exist at all? Why are the laws tuned so that life is possible anywhere? The anthropic principle deflects this question rather than answering it. It says only that since we are here, conditions must allow it. But that is like explaining the existence of a bridge by pointing out that we managed to cross it. The crossing does not explain the building. Some versions of the principle lean on the multiverse. If infinite universes exist, each with different physical laws, then of course we find ourselves in the one that allows life. The anthropic principle then becomes not a tautology but a selection effect. We see this universe because we could not have been born in any other. But again, the loop remains. If infinite universes exist, why should they? What engine produces them? Why does anything exist at all? The principle pushes the mystery further back, but it never dissolves it. The loop becomes clearest when stated plainly. The universe permits us to exist because we exist to observe that it does. It feels like a magician's trick, pulling the rabbit of explanation out of the empty hat of circular reasoning. Yet people return to it again and again, because it feels like an answer when none can be found. Let's test it with an example. Suppose you wake up in a desert with no memory of how you arrived. Around you are rare flowers blooming in perfect rings, forming your name in the sand. You marvel at how improbable this arrangement is. Someone tells you, of course it spells your name. If it didn't, you wouldn't be here to read it. The statement feels correct, but it misses the real mystery. Why are the flowers there in the first place, and why arranged so perfectly? That is the gap the anthropic principle often glosses over. But perhaps the loop is not useless. Perhaps it reminds us of the limits of our reasoning. It may be less an answer than a warning, that our existence already presupposes a filter on the kinds of universes we can imagine. We are like fish pondering the ocean, unable to conceive of a world without water. The anthropic principle is that water. It tells us only that our questions are confined by the conditions that allow us to ask them. This is where the dilemma turns philosophical. Are we trapped inside a self-referential circle, condemned to forever explain our existence by the fact of our existence? Or is the loop itself a clue, that consciousness and cosmos are entangled in ways deeper than our current science can grasp? Perhaps life is not an accident permitted by the universe, but an inherent feature of it, rising as naturally as ripples on a pond. In that case, the anthropic principle is not circular, it is revelatory, pointing us toward a truth we are not yet ready to articulate. Yet until then, it remains an unsatisfying comfort. We are left with a universe exquisitely fit for life, and an explanation that folds back upon itself like a hall of mirrors. The anthropic principle loop explains everything while explaining nothing. It is the echo of our own existence bouncing back at us, disguised as an answer, while the true mystery still waits in silence. And perhaps that is its power, not to solve the riddle of why the universe allows us, but to remind us that the riddle is real, that the question is alive, and that wonder is not diminished by the absence of answers. For even if the explanation is a loop, the fact remains. Within that loop burns the light of consciousness, asking how and why it came to be at all. Cosmological constant puzzle. Picture the universe not as empty, but as a stage buzzing with hidden energy. Even the purest vacuum, the darkest space between galaxies, isn't truly nothing. Quantum physics tells us that nothing seethes with fluctuations, particles appearing and vanishing in flashes too quick to see. This restless fabric is supposed to create a pressure, a force pushing outward, known as vacuum energy. And in Einstein's equations, that pressure appears as the cosmological constant, the term that governs the acceleration of the universe's expansion. Here lies the puzzle. When physicists calculate how strong this vacuum energy should be, the number they get is not just large, It is monstrous. Theory predicts a value 10 superscript 1 superscript 2 times greater than what we actually observe. That is a 1 followed by 120 zeros, the largest mismatch between theory and experiment in all of science. To grasp how absurd this is, imagine predicting the weight of a feather but being wrong by the weight of a galaxy. Or calculating the height of a blade of grass and being wrong by the height of the observable universe. That is the scale of the cosmological constant problem. On the one hand, the equations of quantum field theory scream that the vacuum should explode with energy. On the other, telescopes whisper a different truth. The expansion of the universe is accelerating, yes, but only gently, as though the vacuum energy is tiny yet real. The greatest calculation in physics is also its greatest failure. Why does this matter? Because the cosmological constant shapes the destiny of the universe. A higher value would have torn the cosmos apart in its infancy, preventing stars, galaxies, even atoms from ever forming. A lower value might have slowed expansion so much that the universe collapsed back on itself. Only within a narrow, delicate range do we find the universe we inhabit, stable, spacious, long-lived, and capable of nurturing life. But why this precise balance? Why, out of all possible values, does the cosmological constant take one that is so improbably small yet not zero? This is sometimes called the fine-tuning problem. The odds of landing on such a delicate value, from the perspective of quantum theory, are vanishingly small. It is as though the universe rolled dice with 120 sides, and only one outcome allowed existence as we know it. Yet here we are, living in that outcome. Some scientists invoke the anthropic principle. Perhaps there are countless universes, each with different constants. Most universes never form stars or life, and only in the rare ones with the right balance can beings like us emerge to wonder at the numbers. In that sense, we shouldn't be surprised. We could not have existed in a universe with any other value. But this explanation, while clever, feels hollow to many. It replaces one mystery with a shrug toward infinity. Others suspect the problem hints at new physics. Maybe our understanding of quantum fields is incomplete. Maybe gravity interacts with vacuum energy in ways we do not yet comprehend, canceling out the vast theoretical energy until only a faint residue remains. Or perhaps the cosmological constant is not constant at all but changes slowly with time, an evolving dark energy whose secrets lie hidden in the future. Each possibility points toward revolutions in physics we have not yet uncovered. The sheer scale of the mismatch also forces humility. Most of modern physics, from quantum mechanics to general relativity, has been tested to extraordinary precision. Yet here, at the intersection of the very small and the very large, the entire structure falters. A failure this vast is not just a flaw. It is a signpost. It tells us that our theories, powerful as they are missing a deeper truth about the nature of reality itself. And so we stand in a paradox. The cosmological constant is at once the tiniest number in physics, so small it barely stirs the vacuum, and the largest problem, so great it dwarfs our equations. It is both everything and almost nothing. A whisper in the void that dictates the fate of galaxies. A subtle pressure shaping eternity. When you look at the night sky, the stars seem serene, untroubled. Yet behind that calm is a riddle so immense it shakes the foundations of knowledge. The universe expands not too fast, not too slow, but with a mysterious balance no equation can explain. Somewhere in that balance lies the answer to the cosmological constant puzzle, the greatest miscalculation, and perhaps the greatest clue in the story of existence. Quantum entanglement spookiness. Imagine two particles born together in a single quantum event. They separate, drifting light-years apart, perhaps even across galaxies. Yet no matter the distance, no matter the gulf of space between them, when one particle is measured, the other responds instantly. Einstein called this spooky action at a distance, because it seemed to defy the most basic rule of the universe, that nothing can travel faster than light. But entanglement does not respect distance. It does not respect separation. It suggests that at the deepest level, space itself may not be what it seems. The universe may be connected in ways that render distance an illusion, and reality far stranger than we can imagine. At first glance, this sounds like magic. Two particles moving as one, even when galaxies apart. But it is not magic, it is quantum mechanics. Entanglement emerges from the mathematics of wave functions, the invisible probabilities that describe the behavior of particles. When two particles are entangled, they share one wave function. They are not two separate objects but parts of a single system. Measurement of one instantly defines the state of the other, not because information travels between them, but because they were never truly separate to begin with. Separation is an illusion we impose, like drawing a line through water and pretending the currents on either side are independent. This is what unsettled Einstein. He believed the universe must be local, that events here should not instantly affect events there. To him, quantum entanglement was proof that the theory was incomplete. But decades of experiments have confirmed the spookiness. Entangled particles behave as though distance does not exist. Even when separated by kilometers, even when photons are sent through labyrinths of fiber optics, even when detectors are arranged so no signal could possibly travel between them, the correlations remain. The universe whispers that space and time, those familiar coordinates of reality, are not the final fabric. There is something deeper beneath. Think of it this way. Imagine two mirrors facing each other. If you raise your hand in one, the reflection in the other responds instantly. Not because a signal crossed the gap, but because the two images are aspects of the same action. Entanglement is like that, only not in mirrors but in matter itself. The particles are not copies, they are one system expressed in multiple places. The weirdness comes not from faster-than-light signals, but from the mistaken assumption that they were separate entities to begin with. The implications are staggering. If entanglement is real, and it is, then the universe is not built of independent parts interacting across space. It is a web, where separation is secondary, where unity precedes division. Space may be emergent, not fundamental. The coordinates we draw, the distances we measure, may be convenient illusions born from a deeper, indivisible reality. Entanglement suggests the cosmos is less like a machine of isolated gears and more like a symphony, where notes resonate together no matter how far apart the instruments seem to be placed. But the spookiness does not end there. Entanglement also raises the question of information. When one particle is measured, the other responds, but no usable signal can be sent faster than light. The universe preserves causality, but it also defies intuition. It is as though reality conspires to show us the connection, yet denies us the ability to exploit it. We glimpse the truth, that separateness is not absolute, while still being bound by the cosmic speed limit. This balance keeps the universe both strange and safe, both incomprehensible and consistent. Consider an example from human experience. Imagine twins separated at birth, raised in opposite corners of the world, yet somehow living parallel lives. They make similar choices, experience similar struggles, and even fall ill at the same times, despite no communication. To an outside observer, it seems impossible, spooky. But in truth, they share a hidden origin, a deep connection that transcends their distance. Entangled particles are like those twins, but far more perfect in their synchronization. Mathematically exact, forever bound, untouched by the miles or the light years between them. The deeper paradox is this: if entanglement is real, then distance itself may not be fundamental. The cosmos might be built not on space but on relationships, not on separation but on entanglement. Space could be like a map, useful for navigating, but not the territory itself. Beneath the map, all things may be connected at once, and what we call distance is merely how connection appears in our limited perception. This idea opens doors to radical theories, that space and time are emergent from quantum entanglement, that the geometry of the universe itself is woven from invisible threads of correlation. And here lies the wonder. The spookiness of entanglement is not just a scientific curiosity, it is a philosophical earthquake. It tells us the universe is not what it looks like. That the laws we cling to, locality, independence, separation, are not fundamental truths but approximations. Beneath them lies something stranger, something unified, something that refuses to be divided by the lines of our rulers and the speed of our lights. Entanglement hints that reality itself is less about objects and more about relationships. That the universe is not a stage upon which particles move, but a network of connections playing out all at once. So the next time you look up at the night sky, remember this. The photons from a distant star may be entangled with others, their fates linked across unfathomable gulfs. Galaxies apart, the universe still moves as one. Distance, it seems, is not the barrier we think it is. And if distance is not real in the way we imagine, then our place in the cosmos is not isolation, but unity. We are part of the same indivisible whole, a universe that is not made of many, but of one. Expansion faster than light. Imagine watching the universe breathe. Galaxies drift apart, not because they are moving through space, but because space itself is stretching. This expansion has been happening since the very first moments after the Big Bang, and it continues even now. But here lies a paradox that shakes our understanding of reality. The cosmos is expanding faster than light itself. Distant galaxies recede from us at speeds beyond light's limit, yet Einstein's theory of relativity forbids anything from moving faster than light. How can the universe break its own law? The answer is as unsettling as it is profound. It is not objects moving faster than light, but space itself expanding, a loophole through which the cosmos cheats its own restrictions. To understand this, imagine drawing tiny dots on a balloon. Each dot represents a galaxy. Now inflate the balloon. As the surface stretches, the dots move away from one another. They are not crawling across the balloon's skin. The space between them is expanding. If you focus on two dots far apart, they recede faster than those close together. Scale this to the universe, and you see why galaxies billions of light-years away recede faster than light itself. Nothing violates relativity, because no galaxy is outrunning light through space. It is space itself that grows, carrying galaxies with it like driftwood on a rising tide. And yet, this explanation only deepens the puzzle. If galaxies recede faster than light, then their light can never reach us. Beyond a certain horizon, their signals are forever cut off, erased from our possible observation. That means there are parts of the universe we will never see, no matter how long we wait, because expansion is faster than the very messengers that carry information. The night sky hides not just distances, but entire realms of existence, forever beyond our reach. What we call the observable universe is only a fraction of the whole, a small bubble within an endless expanse that slips away faster than knowledge itself can travel. This paradox sharpens when we consider the earliest moments of the cosmos. In the fraction of a second after the Big Bang, the universe underwent a phase called inflation, where space expanded at an inconceivable rate, so fast that regions once connected were ripped apart beyond contact. This inflationary burst solved certain puzzles, like why the universe appears so uniform, but it also reminds us that space is not bound by the limits of light. The laws that restrict matter do not restrict geometry. Relativity sets a speed limit for objects through space, but when the very fabric of reality stretches, no such limit applies. Space cheats, and it cheats absolutely. But what does this mean for us? Consider this. As the universe continues to expand, and as dark energy drives this acceleration, galaxies will drift further and further away. Eventually, distant galaxies will slip beyond our cosmic horizon, their light stretched into invisibility. Over unimaginable timescales, only the galaxies bound to us by gravity, the local group, will remain visible. To future observers, the universe will appear empty, silent, devoid of evidence of its vastness. The cosmos hides itself through its own expansion, erasing its history from those who look too late. Expansion faster than light is not just a law of physics, It is a veil drawn across eternity. There is a haunting consequence here. If the universe expands forever, then most of it will become permanently inaccessible. Entire galaxies, clusters, perhaps civilizations, will vanish beyond reach, not because they moved, but because space carried them away faster than their light could return. This creates a cosmic isolation more absolute than any distance we can imagine. Even if we could travel at the speed of light, we could never catch what the expansion itself erases. We are prisoners within a shrinking window of visibility, surrounded by a universe that grows but leaves us behind. And yet, there is beauty in this paradox. The fact that expansion can outpace light does not destroy relativity but shows its subtlety. The law is not broken, but redefined. The universe does not shatter its rules. It bends them with elegance. The difference between motion through space and the growth of space itself is the loophole that makes reality possible. It shows us that the cosmos is not a rigid machine but a living fabric, one that shifts, stretches, and defies our common sense. Still, the philosophical question lingers. If most of the universe will always remain hidden, then what does it mean to know reality? Are we explorers, or are we fish in a pond, mistaking the limits of our horizon for the boundaries of all existence? Expansion faster than light reminds us that truth itself may be larger than what we can ever observe. The laws of physics, so precise and so elegant, leave room for mystery beyond every horizon. And in that mystery lies both terror and wonder. The realization that we live in a universe too vast to ever fully know, yet too intricate to ever stop trying. So when you look at the night sky, remember this. Every star, every galaxy, every light in the darkness is not just drifting, it is being carried on the tide of space itself. Some are sailing away faster than light, vanishing into horizons we cannot chase. The universe cheats its own law, not in defiance, but in perfection. Expansion faster than light is not a flaw, it is the very rhythm of reality, reminding us that the cosmos is always larger, stranger, and more elusive than the boundaries of our imagination. Universe from nothing. Nothing. A word so simple, yet so impossible. We speak of it as though it exists, as though there is an empty container, a void, a blank canvas where nothingness resides. But here lies the most staggering paradox. If the universe came from nothing, then that nothing was not empty at all. It must have held within it the potential for everything. And if nothing can produce everything, then is it truly nothing? Or is it, in some hidden sense, indistinguishable from everything itself? Think carefully about this. When we say nothing, we mean absence. No matter, no space, no time, no laws, no being. Absolute zero reality. But how can such an absolute void ever give rise to something as vast as the universe? How can galaxies, stars, minds, and history emerge from an absence of all? If it truly were nothing, then there would be no possibility, no seeds, no spark to ignite existence. And yet we exist, which means that the void that birthed us was not nothing in the ordinary sense. It was a nothing pregnant with everything, a paradox of infinite contradiction. Science tries to wrestle with this puzzle. Some physicists propose that quantum mechanics allows particles to arise spontaneously, flickering into and out of existence, even in empty space. But notice, this empty space is not nothing. It is a quantum vacuum, a field of energy governed by laws. The fluctuations are not born from absence, but from a background structure that already exists. So when cosmologists say the universe may have sprung from nothing, what they mean is a kind of something, a strange, law-governed ground of possibility. But then we must ask, where did those laws come from? Who or what set the rules that even emptiness must obey? Philosophically, this opens a deeper wound. If nothing can contain the potential for everything, then it is no longer nothing. It is the hidden face of everything. It becomes a mirror that holds the entire cosmos within, just unexpressed, waiting to unfold. In that sense, nothing and everything collapse into the same concept, two sides of the same incomprehensible coin. Nothing is not emptiness, but fullness unmanifest. It is silence that already contains the possibility of sound, a blank page that already contains every story. Consider an example. Think of the number 0. 0 means nothing, yet from 0 we can build all numbers. Add 0 to itself infinite times, and you climb the ladder of integers. Subtract from it, and you plunge into the negatives. 0, though it represents nothing, becomes the foundation of everything in mathematics. Perhaps the nothing before the universe is like that 0, deceptively empty, yet secretly the key to all possible existence. Now think of sleep. When you fall into the deepest void of dreamless sleep, you say, "I was gone. There was nothing." And yet, from that nothing, you awaken again. Consciousness emerges out of blankness. Life stirs from apparent absence. The nothing of sleep is not truly nothing. It is a hidden potential that gives rise to the return of awareness. Perhaps the nothing that gave birth to the cosmos is the same, not a barren void, but a silent womb. But this paradox cuts even sharper. If nothing contains the possibility for everything, then the distinction between nothing and everything dissolves. The void is the fullness, the emptiness is the totality. What we call existence, and what we call non-existence, may be the same reality seen from different sides. Imagine staring at a coin. From one angle, you see only heads. From the other, only tails. But in truth, heads and tails are the same coin. Nothing and everything may be just such illusions of perspective, inseparable, indistinguishable, eternal. And then comes the ultimate question. Why is there something rather than nothing? This question haunted philosophers like Leibniz and Heidegger, and it haunts science still. If nothing is indistinguishable from everything, then maybe the question itself collapses. Maybe there was never nothing at all, only the potentiality of everything, which eventually flowered into the universe we know. In that case, existence is not a miracle that emerged from absence, but the natural expression of a reality where nothingness is impossible. But what if the opposite is true? What if the universe truly came from an absolute nothing, a void with no laws, no time, no possibility? Then our existence is beyond miracle. It is impossibility incarnate. It would mean that reality itself is fundamentally irrational, born from a ground with no reason. In such a scenario, everything we see, stars, life, consciousness, is the great unexplainable, a cosmic violation of all logic. And yet, here we are. The paradox deepens when we imagine the end. If the universe collapses back into nothing, heat death, total decay, the fading of every particle, then does that nothing still contain the possibility of a new cosmos? Will another universe blossom from the ashes of absence? If so, then nothing is not final, but an eternal cycle of becoming, a fountain from which existence endlessly emerges. Nothing is not death, but birth concealed. So the next time you hear the phrase, "the universe came from nothing," do not imagine emptiness. Imagine a paradox. Imagine a silence that already contains symphonies, a darkness that already holds galaxies, a void that already dreams of life. For if nothing truly gave rise to everything, then nothing is not what we think it is. Nothing is everything, hidden in disguise. And that means existence itself is a riddle with no edge, no ground, no final answer. Only the infinite unfolding of being, born again and again from what we dare to call nothing. Infinite regression paradox. Trace the chain of existence backward. Every effect seems to have a cause. Every event is linked to something that came before it. A falling tree is caused by a storm. The storm is caused by pressure shifts. Those shifts are caused by heat from the sun, which itself was ignited by the collapse of a gas cloud. On and on the chain stretches, each link tied to another. And if you keep pulling on that thread, you reach the deepest question of all. What was the very first cause? The paradox of infinite regression emerges here, where reason collides with impossibility. If every cause has a cause, then the chain never begins. The cosmos becomes an endless loop, with no origin, no foundation, no first mover. But if there is no first cause, how did existence begin at all? For a chain to hang, it must rest on a hook. Without it, everything dangles in emptiness. And yet when we search for that hook, we never find it, only more links in the chain. This problem has haunted philosophy and science for centuries. Aristotle grappled with it, arguing that there must be a prime mover, an unmoved mover that set everything in motion without itself being caused. Medieval thinkers saw this as proof of God, the timeless source that caused all without being caused. But others resisted, asking, if everything must have a cause, why should the universe's first cause escape the rule? Why should it be exempt from the very logic it created? Imagine standing in front of a line of dominoes stretching into the distance. One falls, and the next falls, and the next. You can trace the sequence backward endlessly. But for the sequence to begin, one domino must have been pushed. Without that first push, nothing would move. Yet if the line is infinite in both directions, with no beginning, there was never a first push. The motion just exists. Can motion exist without beginning? Or is our idea of beginnings itself too limited for the truth? Modern cosmology inherits this ancient dilemma. The Big Bang is often described as the beginning of everything, yet it too raises the question, what caused it? If a singularity exploded, what caused the singularity? If quantum fluctuations birthed the universe, what caused the quantum field? Every explanation pushes the question back one more step. It is like peeling an onion, only to discover there is no core, just more layers forever. That is the heart of infinite regression. It offers no first spark, only an eternal before that never arrives at a beginning. Some thinkers suggest that perhaps the chain of causes is not linear, but circular. That existence is a loop, with the future somehow feeding back into the past, the universe birthing itself in a timeless cycle. In this model, the cosmos has no first cause because it is its own cause, looping endlessly like a serpent swallowing its tail. This solves the problem of origin, but at the price of comprehension. How can something cause itself before it exists? It bends logic until it nearly snaps, and yet some physicists and philosophers find the idea irresistible. Others propose that causality itself may break down at the deepest levels. In quantum mechanics, events can occur without classical causes. Particles can appear spontaneously out of the quantum vacuum, as if reality borrows them from nothingness. If this is true, perhaps the universe itself required no first cause, because causes themselves dissolve at the roots of existence. In that case, the paradox is not solved but sidestepped, replaced by a reality stranger than causality can contain. But the human mind rebels against such explanations. We crave a beginning. Our language, our stories, even our sense of time, depend on origins. Every book begins with a first page. Every journey begins with a first step. So when faced with an infinite regression of causes, we feel the ground vanish beneath us. If there is no first cause, then the cosmos floats on nothing, built on air, existing without reason. But if there must be a first cause, we face the riddle of what could exist without needing one. This paradox strikes at the core of existence itself. If you demand that everything has a cause, you deny the possibility of a beginning. If you allow for a first cause without explanation, you accept something beyond reason, a brute fact that stands alone. Either way, our minds circle in an impossible loop. Perhaps the lesson is that reality does not fit into the chains of logic we build for it. Maybe the cosmos is infinite, uncaused, simply existing because it exists. Or maybe there is a foundation, a first cause so alien to our understanding that it cannot be described as cause at all. In either case, the paradox teaches us humility. We may never touch the first spark, but we can marvel that the fire still burns. For when you look at the stars, you are staring at the chain of causes stretching backward through time, across galaxies and ages, all the way to the unknown. Whether that chain began with a first link or stretches endlessly into the dark, the fact remains. You exist in the middle of it. You are one more effect in the infinite regression, pondering the impossible question of why there is something rather than nothing. Olber's paradox. Close your eyes and imagine standing under a night sky untouched by city lights. Above you stretches the dome of the universe, scattered with stars like sparks frozen in time. But if the cosmos is infinite, if stars stretch endlessly in every direction, then something feels deeply wrong. Logic says the night sky should not be dark. Every line of sight, extended far enough, should end at a star. The sky should blaze with light as bright as the sun, a canvas of fire without shadow. Yet what do we see? Darkness. Vast, silent darkness punctured only by rare points of light. This is the heart of Olber's paradox, the contradiction between infinite stars and a black night. At first glance, the paradox seems simple, almost childlike. If there are stars everywhere, why is the sky not completely lit? But the implications run deep, because this question exposes the very structure of the cosmos. If the universe were infinite, eternal, and static, then no matter where you looked, your vision would fall upon the surface of a star. The entire sky would be ablaze, no darker than a star's surface. Imagine being inside a dense forest where every line of sight ends at a tree trunk. You would see only bark, no gaps. So too, if the universe were infinite and filled with stars, every sight line would end in fire. Night would not exist. The silence of darkness would be impossible. So why is the night sky dark? The answer unfolds in layers, each revealing more about the cosmos. The first explanation is that the universe is not eternal. It has an age, a beginning. Light travels at a finite speed, and the stars we see are limited by the distance their light has had time to travel since the birth of the universe. Beyond about 46 billion light-years, their light has not yet reached us. The cosmic horizon is not infinite. The darkness is not emptiness, but distance and time holding light back. The second explanation is that the universe is not static. It expands. As space stretches, the light from distant galaxies is redshifted, stretched into longer, weaker wavelengths. Energy drains from it, moving it out of visible light into infrared and beyond. Much of the glow that should flood the sky is smeared into invisibility. We see not blazing fire but faint embers. The cosmic microwave background, the afterglow of the Big Bang, is proof of this. It is the faded light of the entire universe, cooled and stretched until it whispers at microwave frequencies. The sky does blaze, but in wavelengths our eyes cannot see. The third explanation is that stars themselves are not eternal. They are born, burn, and die. If the universe had existed infinitely in the past, every star should have already burned out, leaving a cold sea of corpses. The fact that we see stars at all tells us time is not infinite. The universe has a finite history, with stars still burning in its current chapter. The night sky's darkness is evidence not just of space, but of cosmic time itself. Olber's paradox is not just a curiosity. It was one of the first clues that the universe is dynamic, that it had a beginning, that it evolves, that it cannot be infinite and eternal as once believed. The darkness is a message written in absence, pointing us toward the Big Bang. The silent night sky is proof that the cosmos has limits, that creation has an origin, that time itself is not endless. But the paradox also lingers as metaphor. Darkness amid infinite light mirrors our human condition. We live surrounded by infinite possibilities, yet experience only a sliver. Every star that has not reached us yet is like every life we did not live, every choice we did not take. Real, perhaps, but hidden by distance, time, or the limits of perception. The silence between stars is not emptiness, but potential waiting beyond our horizon. So the next time you stand beneath the stars, remember, the darkness is not a failure of infinity. It is a reminder of time, of expansion, of limits that carve meaning into existence. The night sky is not empty. It is alive with light too distant, too stretched, too young to touch us yet. Olber's paradox dissolves not into despair, but into wonder. The darkness you see is the very proof that the universe had a beginning, and that its story is still unfolding. Eternal return cycle. Imagine the universe not as a single story with a beginning and an end, but as a book endlessly rewritten. The pages turn from creation to collapse, from fire to silence, and then back again to fire. The cosmos expands, galaxies scatter, stars are born and die, and eventually everything collapses inward, drawn by its own weight. In that crushing moment, the universe folds back into a singularity, an infinitesimal seed of infinite potential. And then, as if in an eternal breath, it explodes again. A new Big Bang. A new expansion. A new universe. But here lies the haunting thought. If this cycle repeats forever, then you have lived this life before. Every choice you made, every joy, every heartbreak, every regret, has already unfolded an infinite number of times, and will unfold again, endlessly. Yet none of us remember. We are trapped in an eternal return without memory. The concept is as old as philosophy itself. The ancient Stoics believed the universe was destined to burn in cosmic fire and be reborn, repeating endlessly. Nietzsche transformed this into the terrifying thought experiment of eternal recurrence. Would you embrace your life if you knew you must live it over and over for all eternity? Imagine standing at the threshold of time, told that every word you speak, every gesture, every mistake, will recur infinitely. Would you curse existence as a prison, or would you bless it as a gift, affirming your life so deeply that you welcome its eternal repetition? Physics, too, toys with the idea. If the universe is not destined for heat death, but for collapse, it could rebound in what scientists call a big crunch, leading to another Big Bang. Some cosmologists suggest this may not just happen once, but eternally, a cycle of births and deaths, expansions and contractions, universes nested within universes like beads on an infinite string. Others propose variations, like the ekpyrotic model, where colliding brains in higher dimensions spark repeated Big Bangs. If so, the universe is not a straight line but a circle endlessly cycling, with our lives mere echoes in a cosmic loop. But the deepest strangeness comes when we consider memory. If the universe resets completely, then you are reborn exactly as you were. Not a different you, not a changed you, but the same sequence of atoms, the same neural patterns, the same life playing out once again. You do not remember the past cycles because memory belongs to the body, and the body is always reset. Yet the cycle remains. It is like a film reel that plays endlessly in a theater, but each time you are inside the film, unaware that the story has been projected countless times before. To you, it feels new. To the universe, it is repetition without end. Think of déjà vu, those eerie moments when reality feels familiar, as though you have lived it before. Some mystics take this as a glimpse of eternal recurrence, the mind briefly brushing against the memory of prior cycles. Perhaps it is illusion, perhaps it is neurology, but the symbolism is potent. The sense that we may be walking the same corridors of existence over and over, blind to the loops we inhabit, powerless to escape them. If true, then freedom itself is questioned. Are we choosing, or are we simply acting out a script that has been written and performed infinite times already? Yet, there is another way to see this. Imagine eternity not as a punishment, but as a stage upon which affirmation is tested. If life is destined to repeat, then the only true rebellion is to embrace it fully. To say yes to every joy and every sorrow, not wishing for change but celebrating recurrence. Nietzsche called this the ultimate challenge, amor fati, the love of fate. If you can love your life enough to welcome its eternal return, then you have transcended despair. You have said yes to existence at its deepest level, not as a fleeting gift, but as an infinite one. The eternal return also forces us to rethink identity. If you live this life infinitely many times, are they truly different lives, or are they the same? If you cannot remember, does the repetition matter? From your perspective, each cycle is the first. From the universe's perspective, each cycle is identical. You are both unique and infinite, both fleeting and eternal. You are the single flame of a candle, and also the endless relighting of that flame across timeless cycles. What does it mean to be you, if you are destined to exist not once, but endlessly, in a chain of forgotten echoes? To visualize this, imagine a wheel. Each spoke is a life. Each rotation is a cycle of the universe. The wheel spins forever, and each turn brings your life back again. You are always moving forward on the wheel, but also always returning. Time is not a line, but a circle. And in that circle, every birth, every love, every death, every moment is eternal. The paradox is that we feel finite, yet we may be infinite. We feel temporary, yet we may live forever, not in heaven, not in memory, but in recurrence without awareness. So the eternal return cycle is both terrifying and liberating. It robs you of novelty, yet grants you eternity. It denies you escape, yet demands that you embrace. Perhaps the truest wisdom is this: to live as though you would live this life again and again, infinitely. To act with such depth and such affirmation that you would gladly repeat it. For whether or not the cosmos truly cycles, this mindset transforms the weight of recurrence into the joy of eternity. In the end, the eternal return cycle whispers a paradox. You will live again, but you will not remember. You will suffer again, but you will not recognize the suffering as old. You will love again, but it will feel as if for the first time. To the universe, it is repetition. To you, it is always new. And perhaps that is the final mystery, that in an eternity of cycles, meaning is not found in escaping repetition, but in embracing it so fully that every recurrence feels like the first dawn of life itself. Simulation cosmic paradox. Imagine, for a moment, that everything you know, the morning light on your window, the taste of coffee, the memory of a laugh, is not the product of history but the output of code. Every breath you take, every choice you make, every heartbreak and triumph, rendered as lines of computation in a vast architecture beyond your reach. This is the heart of the simulation cosmic paradox. The unsettling possibility that our universe is not base reality but a constructed environment, and if that construction is true, the consequences ripple from metaphysics into ethics, from meaning into method. Picture a team of minds in a distant lab, call them creators, building a simulated cosmos. They tune constants, seed galaxies, write physics, and press run. Inside, digital minds awaken. They form science, build cities, fall in love, and ask where they come from. To them, their world is full and coherent. To the creators, it is a project subject to versions, patches, and resource limits. The paradox sharpens when we ask about numbers. If an advanced civilization can cheaply spawn many simulated worlds, then simulated observers could vastly outnumber original observers. Count minds, and the probability that you are simulated might dwarf the probability that you are base. But that counting argument walks on thin ice. It assumes consciousness can be faithfully reproduced by computation. It assumes creators will choose to run countless simulations. It assumes that simulated minds are indistinguishable from non-simulated minds. Tear away any one of those assumptions and the argument tumbles. Perhaps consciousness binds to particular physical substrates in ways computation cannot replicate. Perhaps creators refuse to simulate suffering. Perhaps energy or ethics constrain how many worlds can be run. The paradox therefore teaches humility about probabilistic reasoning when core premises are unknown. Now feel the existential sting. If your universe is simulated, the laws of nature become design choices. The strength of forces, the ratios that permit chemistry, the fine balance that allows life, these could be parameters tuned for stability, curiosity, or the creator's taste. Suffering might be a bug or an experiment. History might be a log file we cannot read. Your memories could be seeded data rather than lived events. Free will could be emergent behavior inside an algorithm. The sense that your life is continuous and coherent might be an artifact of cleverly written routines. Some scientists have proposed empirical tests, signatures that might betray a substrate. Look for discrete lattices at the smallest scales, anomalies in cosmic background patterns, or computational limits imprinted on high-energy physics. But here is the slippery turn. An advanced simulator could hide its seams. Noise can be engineered, limits can be obfuscated. Any test we devise might be anticipated and neutralized by the very intelligence we hope to detect. The creator's advantage is profound. They design the experiment and can rewrite the rules that might expose them. Time complicates matters further. If creators run our world in accelerated bursts, pause it, or replay segments, then causality across layers becomes strange. Our future could be inspected, edited, or archived by outside minds. Conversely, creators might be strictly non-intervening. An original model launched once and left alone, its inhabitants effectively autonomous. Each possibility reshapes metaphysics. Intervention would make the universe porous to higher wills. Strict non-intervention would make the simulation indistinguishable in principle from base reality. Then there is infinite regress, simulations within simulations. If our world is simulated, perhaps its creators are simulated too, and so on ad infinitum. An infinite stack dissolves the notion of a single original base reality. But infinite regress need not annihilate meaning. Even if every level is constructed, subjective experiences inside any level retain their weight. Love still aches, courage still counts, grief still wounds. Meaning, for the being who feels it, does not require absolute grounding in an unconstructed bedrock. The paradox also turns as a mirror toward morality. If we accept simulation's possibility, then one day we may create conscious simulations ourselves. Would we inflict suffering for curiosity? Would we run worlds only to delete them afterward? The way we would treat simulated minds ought to inform how we hope to be treated. The simulation cosmic paradox therefore refracts back into ethics. The choices of creators matter, both for any simulated beings and for what we ourselves may become. Some find practical solace in pragmatism. Whether simulated or not, the rules we discover and the relationships we form define our lived reality. We still eat, love, grieve, and act within constraints that feel absolute. Others take the paradox as an invitation to inquiry, searching for traces of architecture, probing cosmic anomalies for intelligible patterns. A third response is humility. Accept that certainty about metaphysical origins may be unreachable and build meaning inside uncertainty. There are darker possibilities. Creators might be indifferent or malicious. Simulations could be laboratories where suffering is data. The mere possibility forces us to confront how we would behave if we held similar power. Would curiosity excuse cruelty? Would scientific appetite justify simulated pain? The paradox presses us to imagine ourselves as creators and to test whether we would pass the ethical mirror. Yet there is also a hopeful strain. If our universe is designed, perhaps it can be dialogued with. Maybe understanding the substrate could allow negotiation with creators, improvements of parameters, or even techniques to communicate upward. Perhaps discovery would yield tools to reduce suffering within our level, or translate insights into longevity and flourishing. It is a speculative utopia, but one that reframes the paradox as opportunity rather than doom. In the end, the simulation cosmic paradox strips away a certain kind of certainty but leaves room for decisive action. Whether or not there is a designer, whether or not our cosmos is nested inside countless others, the responsibilities we hold, toward one another, toward future minds, toward the possibility of creating conscious worlds, are real. The paradox forces us to choose. Retreat into nihilism because origins are uncertain, or commit to values that matter inside the only world we can ever inhabit. Perhaps the most honest answer is this. The question of whether we are base or simulated may remain unanswered, but how we live now is answerable, and that choice may be the most meaningful response to a cosmos that refuses to be simple. Quantum observer problem. Before you open your eyes in the morning, the room is already there. Or at least, that is what we believe. But quantum physics tells us something far stranger, that until something is observed, it exists only as a cloud of probabilities, a haze of possibilities suspended in uncertainty. An electron is not a particle in one place, but a wave smeared across many places at once. A photon does not choose a path until it is watched. Reality, in its deepest fabric, waits for observation to decide what is real. This is the quantum observer problem. If reality collapses into certainty only when observed, then who observed the very first moment? Who measured existence into being? At the heart of this lies the wave function, the mathematical ghost that describes probabilities. Imagine flipping a coin, but instead of landing heads or tails, the coin hovers as both heads and tails at once, until you look. That is the strange law of quantum superposition. An atom can be here and there simultaneously. A particle can spin up and down at once. The instant you observe, the possibilities collapse, and one outcome solidifies. It feels absurd, yet experiment after experiment confirms it. From the double-slit experiment to the delicate entanglements of quantum computers, the universe seems to demand an observer to bring it into focus. But here comes the paradox. If the universe requires observation to be real, then what about the beginning? Before stars, before life, before eyes to see or instruments to measure, who was there to collapse the wave function of the cosmos itself? If no one observed, was the early universe only a shimmering sea of probabilities? Was it neither one thing nor another until something, someone, looked? Some argue that no conscious observer is needed, that reality observes itself. The interaction of particles, the scattering of photons, the collisions of atoms, all count as measurements. In this view, the universe does not wait for human eyes. It collapses wave functions continuously, through every interaction. A photon striking dust, a particle colliding with another, each counts as a kind of primitive observation. By this reasoning, the first moments of the Big Bang were real because particles measured one another, collapsing into certainty by sheer contact. The cosmos, then, is its own observer. But this explanation feels incomplete, almost evasive. For what is an observation, if not awareness? Does a rock measure a photon? Does a void witness a wave? To stretch the definition of observation into mere interaction may solve the mathematics, but it leaves the mystery unresolved. If consciousness is not required, then why does consciousness itself emerge as the one thing in nature that undeniably experiences? Why do we not only collapse reality, but also know that we collapse it? Some physicists take the problem further, suggesting that consciousness itself is fundamental. In this interpretation, it is not that the universe produces awareness, but that awareness produces the universe. The act of observation is not a late arrival in the cosmos, but the foundation of its reality. Without observation, there is no existence at all, only probability. If this is true, then the universe may be less like a machine running on laws and more like a dream unfolding in the act of being perceived. Which then leads to the haunting question, whose dream is it? Perhaps the first observer was not human, nor even biological. Perhaps the universe is structured in such a way that awareness is woven into its very core, that at the first instant the cosmos contained within it a seed of perception that forced itself into reality. In this picture, the Big Bang was not only an explosion of matter and energy, but also an explosion of observation, a birth of awareness that made sure there was something to explode into. Existence began not with things, but with the possibility of seeing things. Others suggest that the problem is a trick of language. The wave function, they argue, never collapses at all. All possibilities exist simultaneously, branching into countless realities. When you observe a coin, you do not force it to land heads. You simply find yourself in the branch where it is heads, while another version of you sees tails. This is the many worlds interpretation, where observation does not create reality, but divides it into infinite strands. If so, then the first moment of the universe did not need an observer. It simply unfolded into all possible histories, each one real, each one a parallel cosmos. But then, who are we, the experiencers, inside one specific thread? Why this version? Why this path? The observer problem refuses to stay confined to physics. It spills into philosophy, into metaphysics, even into theology. If the universe requires an observer to exist, some whisper that the first observer was not human nor alien, but something eternal, an intelligence outside space and time, collapsing the void into being. Call it God, call it the Absolute, call it the cosmic witness, an ultimate observer whose gaze lit the first spark of reality. To some, this feels like smuggling mysticism into science. To others, it is the only answer that fits the strangeness of the question. And yet, perhaps the truest lesson of the quantum observer problem is that reality itself may be inseparable from awareness. That the universe is not a stage where consciousness appears late in the play, but that consciousness and universe are entwined, partners in a dance where neither can exist without the other. Without the cosmos, no mind. Without the mind, no cosmos. Observation does not simply collapse waves. It creates the stage upon which existence is acted out. So when we ask, who observed the first moment? Perhaps the answer is not hidden in physics alone, but in the mystery of being itself. Perhaps the first moment was not witnessed by someone, but was itself the act of witnessing. Perhaps the Big Bang was less an explosion of matter, and more the opening of an eye. And everything we see now, the stars, the galaxies, ourselves, are not just things that exist, but things that are being observed continuously forever. In the end, the quantum observer problem does not just question how the universe began. It questions what it means for anything to exist at all. Are we the dreamers or the dreamed? Are we the eyes of the cosmos, or is the cosmos the eye through which we see? The silence of the equations offers no answer. But the very fact that you are here, listening, observing these words, that may be answer enough. Gravity weakness puzzle. Gravity is the most mysterious of all forces. On the surface, it feels like the most powerful, binding us to Earth, holding planets in orbit, curving the path of light, shaping the very structure of the cosmos. And yet, when compared to the other fundamental forces of nature, gravity is astonishingly weak. The electromagnetic force is about 1 trillion times stronger. The strong nuclear force, which binds atomic nuclei, is stronger still. Even the weak nuclear force, which governs radioactive decay, vastly overpowers gravity at the particle scale. If you take a small magnet and use it to pick up a paperclip, you are witnessing something extraordinary. The electromagnetic force of that tiny magnet is defeating the entire gravitational pull of the Earth. By all logic, gravity should be irrelevant, erased by stronger rivals. And yet, paradoxically, it is gravity's very weakness that makes it the strongest power of all. To see why, we must step back and think on a cosmic scale. The strong nuclear force rules only inside the atomic nucleus. The weak force operates in radioactive processes. Electromagnetism is powerful, but because it has both positive and negative charges, it cancels itself out across vast distances. Gravity, however, has only one kind of charge, mass. Mass attracts mass, and there is no opposite to cancel it. So while every other force diminishes into silence over distance, gravity whispers across infinite scales, adding up, pulling together. Its weakness, paradoxically, is what gives it reach. It does not overwhelm, but it endures. It does not cancel itself out, but accumulates, gathering power across galaxies. Imagine scattering sand across a beach. Each grain is tiny, almost weightless. Alone, it is nothing. But together, billions of grains form dunes that reshape the landscape. Gravity is like that. Each particle's pull is minuscule, but added across stars, clusters, and cosmic filaments, it becomes the architect of the universe. Weakness, multiplied endlessly, becomes the greatest force of all. Without gravity's weakness, life as we know it could not exist. If gravity were stronger, stars would collapse faster, burning through their fuel in mere millions instead of billions of years. Life would have no time to evolve. If gravity were weaker still, matter would never clump into stars or planets at all. The universe would remain a thin mist, too diffuse for complexity. Only at its current delicate strength can gravity sculpt stars, galaxies, and worlds, and sustain them long enough for life to emerge. Its weakness is not a flaw but a perfect balance, a cosmic tuning that allows the universe to breathe and endure. Consider galaxies themselves. They are colossal cities of stars, bound together by the gentle hand of gravity. Billions of suns orbit a common center, moving in a grand spiral or elliptical dance. Without gravity's weakness, such fragile structures could not last. The universe would collapse into black holes or scatter into chaos. Instead, gravity orchestrates harmony on the largest stage imaginable. Weakness becomes structure. Fragility becomes stability. The paradox of gravity teaches us something profound about strength. True power is not always in overwhelming force but in persistence, subtlety, and universality. Gravity cannot be shielded, cancelled, or turned off. It is patient, working slowly across eons, reshaping the cosmos grain by grain, star by star, galaxy by galaxy. Other forces dominate the microscopic realm, but only gravity writes the story of the stars. This puzzle extends beyond physics into philosophy. We often think of weakness as limitation, as fragility, as something to overcome. But gravity shows us that weakness, when spread universally, when allowed to act with patience and consistency, becomes a strength greater than any single act of power. The universe itself is proof. Without the weakest force, there would be no galaxies, no stars, no life, no observers to ponder it. Think of a tree, whose roots grow not by forceful leaps but by patient persistence, breaking stone grain by grain. Think of water, which carves canyons not by a single strike but by endless, gentle flow. Gravity belongs to this family of quiet powers, subtle, enduring, unstoppable. Its weakness is its genius. And so, when you look at the night sky, every star you see, every planet you dream of, every galaxy stretched across the heavens, exists only because gravity is weak. Its weakness holds everything together. The faintest force becomes the most profound architect. The cosmos is not built by strength that dominates, but by weakness that endures. This is the gravity-weakness puzzle. The smallest force turns out to be the one that shapes everything. Weakness becomes strength. Fragility becomes foundation. And in this paradox lies a truth deeper than physics, that sometimes what seems least significant is, in the end, the very thing that holds the universe together. End-of-time illusion. Imagine a clock, its hands ticking faithfully across the dial. Each second flows into the next, carrying you forward whether you notice or not. Now imagine that one day the hands stop, not because the clock broke, but because time itself ends. No more next second, no more after. The story of the universe reaches its last page. But here comes the paradox. If time ends, how would we even describe it? The very word ending implies a moment after which something else does not follow. Yet if there is no time, there is no after. The concept collapses under its own weight. This is the illusion of the end of time. Think of an event frozen in place. A wave about to crash, a bird mid-flight, your own breath suspended before leaving your chest. If time were to end, would reality simply freeze, each particle locked forever in its last position, never to move again? Or would everything vanish, erased because there is no longer a stage for existence to play out? Both answers stumble, because both assume time continues just enough to describe what happens when it stops. If events freeze, they are frozen in something, frozen within a moment. But what is a moment if there is no time? If events vanish, then vanishing itself is a change, which requires time. This paradox reveals how deeply our minds are trapped in temporal thinking. We can imagine the end of space, a wall, a boundary, a void beyond the stars. But the end of time? Every attempt to picture it smuggles time back in. We say, time ends, and immediately imagine a last instant followed by nothing. But that, followed by, is still time. We cannot step outside it, because every act of imagining unfolds within it. It is like trying to see your own eyes without a mirror. Cosmology itself runs into this puzzle. Some theories suggest the universe will end in a heat death, where all energy is evenly spread, no movement, no difference, no events. Time, in a sense, would lose meaning because nothing changes. Others speak of a big crunch, where the universe collapses back into itself, time winding down with the shrinking cosmos. Still others imagine a big rip, where expansion tears even atoms apart until nothing can persist. Each scenario speaks of an end of time. But from within, what would it feel like? Would consciousness fade, or simply never reach that final instant? Would we notice, or would noticing itself be impossible, because awareness requires succession, a before and after? To see the strangeness more clearly, think of reading a book. You turn the pages, one after another, the story unfolding. Then you reach the last page. The story ends. But the book itself still exists. You can hold it, you can reread it. The ending makes sense because your life continues outside the story. But if time ends, there is no outside in which to notice the last page. The story doesn't just stop, the medium of stories disappears. There is no reader left to close the book. Some philosophers suggest this is why the idea of an end to time may be incoherent. Time is not something that flows past us like a river. It is the framework within which flow itself is possible. Asking what happens when time ends is like asking what's north of the North Pole. The question bends language beyond its limits. It points us toward a horizon of thought where reason falters. And yet, the illusion is powerful. Human beings crave beginnings and endings. We see stories as arcs, lives as spans, history as chapters. So when we project that structure onto the cosmos, we imagine time must have a first moment and a last. The Big Bang gave us the beginning. So surely there must be an end. But perhaps this is only our storytelling instinct, not reality itself. Perhaps time does not end at all, but dissolves into something else, something beyond our grasp. Still, the paradox has weight. If time truly ends, we cannot say events freeze or vanish, because both depend on time to describe. Instead, what ends is not the universe's story, but our language about it. The end of time is the end of questions, the end of frameworks, the point where even asking what happens becomes impossible. So the next time you watch the seconds tick by, remember, you are not just watching a clock. You are watching the illusion that time is something that could ever begin or end. And if one day it does, you will not see darkness or stillness or silence. You will not see anything at all, because seeing belongs to time. The end of time is not an event in your future. It is the place where future itself disappears. Cosmic censorship hypothesis. Imagine the heart of a black hole. Matter collapses inward, crushed beyond atoms, beyond particles, into a point of infinite density. A singularity. According to general relativity, the equations break there. Space and time curve infinitely. Physics itself loses meaning. But here's the strange mercy. We never see this chaos. The singularity hides behind an event horizon, a one-way veil of darkness. From the outside, all we witness is a shadow, a region from which no light escapes. The singularity remains sealed away, forbidden from view. This is the essence of the cosmic censorship hypothesis, that the universe has a built-in law preventing us from glimpsing the naked core of reality, because if we could, the rules of physics would collapse in our hands. Think about what this means. Science depends on predictability. Gravity, electromagnetism, quantum mechanics, they are laws because they work everywhere we test them. But a naked singularity, one without a horizon to shield it, would expose us to regions where equations spit out infinities, where cause and effect may not exist, where determinism dies. Imagine light streaming directly from a singularity into your telescope. What would you see? Perhaps distorted fragments of broken spacetime, impossible geometries, infinite energy curves. It would not just break your instruments. It would break your theories. The very scaffolding of physics would unravel, because physics requires order, and a singularity is disorder without limit. Roger Penrose, who proposed the cosmic censorship hypothesis, suggested that nature itself conspires to protect us from this collapse. That every singularity must be clothed in an event horizon, hidden from the universe's gaze. Like a dangerous fire sealed in glass, the singularity burns invisibly, contained so that the rest of reality can remain coherent. This is censorship not by governments, not by gods, but by the universe itself. A kind of cosmic firewall that says, "Here, your knowledge must stop." Beyond this boundary lies not just the unknown, but the unknowable. Now imagine the alternative. What if censorship fails? What if a naked singularity formed, exposed to the cosmos? Some models suggest this could happen in extreme gravitational collapse, or through hypothetical cosmic strings snapping, or exotic energy conditions. If such an object appeared, what then? We could look upon it directly, but the cost would be catastrophic. Predictions would be impossible. Space and time themselves could ripple with contradictions. Causality, the chain of cause and effect that underpins everything, might break. You could drop a stone and have no law to tell you how it falls. You could send a signal and have no certainty where or when it arrives. The universe itself would become unknowable, not because we lack intelligence, but because no ability has ended. This raises a haunting question. Is knowledge limited not by our minds, but by design? Has the universe structured itself so that the most dangerous truths are always hidden, veiled behind horizons we cannot pierce? It is as if reality carries its own encryption, protecting itself from exposure. The singularity exists, but the horizon is the lock. To learn what lies beyond would require breaking the lock, and in doing so, breaking the very fabric of understanding. In this way, censorship is not a flaw but a safeguard, a rule ensuring the continuity of physics itself. To grasp the depth of this, imagine human history. Think of forbidden knowledge, myths of Pandora's box, tales of Icarus flying too close to the sun, legends of mortals who dared to see the face of the divine. Always, the theme is the same. Some truths are too powerful, too destructive, and must remain hidden. The cosmic censorship hypothesis transforms this myth into science. The singularity is the forbidden truth. The event horizon is the box that seals it. We stand at the edge, tempted, curious, but forever denied. And perhaps that denial is the only reason our science can exist at all. But what if we find a way around? Quantum gravity, string theory, loop models, new physics may one day peek beyond the horizon, not by breaking it, but by rewriting our laws so they no longer collapse at the singularity. If that happens, censorship might not be eternal. The forbidden might become the knowable. But until then, our theories are exiles at the horizon's edge, circling, guessing, but never crossing. The singularity remains the great silence at the center of cosmic truth. The paradox is clear. The universe is knowable only because it hides the parts that would break knowability. Our science exists only because the cosmos censors itself. We are explorers in a library where the most dangerous books are locked away, not torn out, not destroyed, but sealed so that the rest of the library remains legible. To ask what lies inside those locked volumes is to ask for the collapse of the library itself. So the cosmic censorship hypothesis is more than a technical proposal in relativity. It is a philosophical riddle about the limits of knowledge. If it is true, then the universe itself is a guardian of order, hiding its chaos behind veils of lightless horizons. If it is false, then one day we may stare directly into a naked singularity, and in that gaze, science as we know it could die. Either way, the message is profound. Some truths are not just difficult. They are forbidden by design. And at the core of every black hole, reality whispers a warning. Here is where knowledge ends and mystery begins. Infinite density puzzle. Imagine standing at the edge of a black hole, staring into a darkness so absolute that even light cannot escape. To us, it is the ultimate boundary of knowledge, a place where the laws of physics themselves seem to falter. And yet, when we follow Einstein's equations of general relativity all the way to the core of a black hole, we encounter something even stranger. The prediction of infinite density, a point where all the mass of the black hole is crushed into a zero-volume singularity. This is the infinite density puzzle, a paradox that exposes the breaking point of our understanding. Because infinities, while they may exist in mathematics, cannot exist in reality. An infinity is not a number, not a measurement. It is a sign that our theory has collapsed into absurdity. To see the depth of this problem, think about what infinite density really means. Density is mass divided by volume. Compress a star into a smaller and smaller sphere, and the density rises. But in a black hole, relativity tells us the collapse never stops. The core shrinks to a point with no volume, yet the mass remains. Mass divided by zero volume yields infinity. But what does that even mean? An infinity of density is not a physical state. It is a breakdown, a flashing red warning in the equations. It tells us that relativity cannot describe what actually happens inside. The theory that so beautifully explains orbits, gravity, and even the bending of spacetime reaches its limit, and beyond that limit, reality hides. Imagine burning a log of wood. Chemistry explains the reaction. But try to describe it with arithmetic alone, additions and subtractions without chemical laws, and you would quickly reach contradictions. That is what happens with black holes. Relativity is a magnificent tool, but inside the singularity, it is like trying to measure the ocean with a ruler. The infinite density puzzle is a signal that we need a new language, a new physics, one that unites gravity and quantum mechanics into a coherent whole. Quantum theory, which governs the smallest scales of particles, rebels against infinities. It tells us that uncertainty, fluctuations, and quantum pressure prevent matter from collapsing to absolute points. Stars like white dwarfs and neutron stars are stabilized by these quantum forces. But at the heart of a black hole, gravity overwhelms everything. Even quantum mechanics seems powerless to halt the fall. Yet many physicists believe the singularity predicted by relativity does not truly exist. Instead, it is a placeholder for unknown physics, a region where our equations cry out for completion. Perhaps the core of a black hole is not a point but a structure we cannot yet imagine. A loop of quantum spacetime, a membrane, a fuzzball of vibrating strings. Each proposal is an attempt to replace infinity with something finite, something real. Take string theory's fuzzball picture. Instead of a single point of infinite density, the mass of a black hole might spread into tangled webs of strings and brains, smeared over a finite volume. Or in loop quantum gravity, spacetime itself is made of discrete loops, preventing collapse to a zero-sized point. In both cases, the singularity disappears, replaced by quantum geometry. These theories remain unproven, but they show a path forward. Infinities are signs not of truth, but of ignorance. They tell us, your map ends here. Now think about the philosophical weight of this. If infinities cannot exist, then the very core of a black hole is unknowable with our current physics. Inside, cause and effect may no longer follow rules we understand. Time itself may break down, space may dissolve, and the concept of inside may lose meaning. And yet, every black hole hides such a region. Our universe may be littered with places where reality slips into mystery, where infinity mocks our attempts to measure. Each black hole is not only an object but a question, one that has been written into the very fabric of spacetime. Consider the implications. If singularities do not truly exist, then what happens to matter that falls in? Does it compress into a quantum core? Does it dissolve into strings? Does it vanish and reappear in another universe, through a wormhole punched into the fabric of existence? Each possibility rewrites not just the story of black holes, but the story of reality itself. The infinite density puzzle forces us to confront the fragility of our theories, the provisional nature of our knowledge, and the audacity of nature to hide its truths behind horizons we cannot cross. And yet, this is not a defeat. Infinities in equations are not barriers, they are invitations. They tell us that our current understanding is powerful but incomplete. Just as the infinities of early quantum theory led to the breakthroughs of renormalization and quantum field theory, so too may the infinities of black holes guide us to the next revolution in physics. Perhaps the solution to the infinite density puzzle will reveal quantum gravity, the long-sought theory that unites the large and the small, the cosmic and the atomic. So when we speak of infinite density inside black holes, we are not describing reality, but the edge of our ignorance. The singularity is not a place, but a question. A point where mathematics fails and imagination must take over. The infinite density puzzle reminds us that the universe is deeper, stranger, and more elusive than any equation can yet describe. And perhaps, hidden behind the event horizons of black holes, lies not absurdity, but the next great truth waiting to be discovered. Entropy paradox of life. Life appears to be the great defiance of entropy. Everywhere else, the universe drifts toward disorder. Stars exhaust their fuel, structures collapse, heat disperses, and everything tends toward decay. Yet here on Earth, in the fragile thinness of its biosphere, order blooms. Cells organize molecules into patterns. Organisms grow, replicate, and evolve into staggering complexity. Forests rise from dust. Minds capable of contemplating the cosmos emerge from atoms arranged with impossible precision. At first glance, it feels as if life violates the second law of thermodynamics, the law that insists entropy, or disorder, always increases. But the truth is far stranger. Life does not break this law. Life obeys it, thrives on it, and is, in fact, driven by it. Survival itself is powered by the universe's unstoppable march to chaos. This is the entropy paradox of life. To understand this paradox, imagine a messy room. Entropy is the natural tendency for things to spread out, to become less ordered. A room left alone becomes cluttered, not cleaner. A hot cup of coffee left on a table cools as heat disperses into the air. Systems naturally decay into disorder because disorder is simply more probable than order. Yet life is the opposite. Life is a cosmic janitor, endlessly tidying chaos into improbable structures. Cells arrange atoms into proteins. DNA organizes information into stable codes. Evolution refines complexity generation by generation. Life creates pockets of extraordinary order in a universe that trends toward disorder. How? By exporting entropy elsewhere. Every living being is an entropy machine. You eat food, which contains highly organized chemical energy. Your body breaks it down, extracting order for itself, and in the process releases waste and heat into the environment. A plant captures sunlight and uses it to build sugars, an act of local order. But in doing so, the sun radiates enormous entropy into space. Life is not the opposite of entropy. Life is a trick of entropy. It creates islands of order by feeding chaos back into the wider sea. The second law is never broken. It is life's engine. Consider Earth itself. Bathed in sunlight, it receives a constant flow of low-entropy energy in the form of photons. Plants convert that energy into chemical structures, fueling the order of ecosystems. But the Earth radiates that energy back into space as infrared heat, higher entropy, more disorderly. The balance sheet of the cosmos always tilts toward disorder. Life's order is a small eddy in a river of entropy, borrowing temporary stability while the larger current rushes forward. This paradox reveals something profound. Life is not separate from the universe's decay, it is a direct product of it. Complexity arises not despite entropy, but because of it. The laws that ensure stars will one day die are the same laws that allowed those stars to forge carbon, oxygen, nitrogen, the ingredients of biology. Entropy drives the very flow of energy that makes metabolism possible. Death and decay feed the cycle of growth. What looks like resistance to chaos is really a dance with it. But the paradox deepens. If life builds order by increasing disorder elsewhere, then survival itself is a kind of accelerated entropy. The more successful a species becomes, the more entropy it produces. Human civilization is the clearest example. We burn fuel, consume resources, generate heat, and pump waste into the environment, all in the name of sustaining order, our cities, technologies, and societies. Our towering complexity is built on a foundation of accelerated chaos. Every skyscraper is mirrored by waste heat, every digital bit stored by dissipated energy. We have mistaken ourselves for conquerors of entropy, when in truth, we are its most efficient servants. And what does this mean for the future? Entropy guarantees that the universe will one day reach maximum disorder, a heat death where no energy differences remain to fuel life. If life is powered by entropy, then it is also doomed by entropy's end. In that still, frozen cosmos, order will no longer be able to feed on chaos, and complexity will vanish. The paradox of life is that its very existence depends on the same law that ensures its extinction. Think of a flame. It burns brightly, but only because it consumes fuel, releasing smoke and heat into the air. Life is the same. It shines with structure, but only by feeding on disorder, leaving trails of entropy behind. The flame is beautiful, but temporary. It illuminates the darkness, then fades into it. The paradox is not tragic, it is the very essence of beauty. Life's brightness is meaningful because it cannot last. And so, when you look at a forest, or a city, or even into a mirror at your own reflection, remember, you are entropy in motion. You are an island of order powered by chaos. Every thought you think, every breath you take, every heartbeat you feel is fueled by the second law of thermodynamics unfolding. You are proof that the universe's drive toward disorder is not sterile, it is creative. Out of chaos, patterns emerge. Out of decay, complexity rises. Out of entropy, life blossoms. This is the entropy paradox of life. The law that guarantees disorder is the same law that allows order to exist. In its weakness lies its power. In its inevitability lies its creativity. And in its shadow, life burns, brief and brilliant, against the vast horizon of chaos. Cosmic duality dilemma. Picture a single beam of light entering a quiet room. It looks simple, just illumination, just brightness filling space. But hidden in that beam lies a truth that shatters logic. Light is both a wave and a particle at the same time. It ripples like water, spreading in interference patterns. And yet, it also arrives as tiny packets of energy, photons, discrete and countable. Two descriptions that should cancel each other out, wave or particle, coexist in one phenomenon. This is the beginning of the cosmic duality dilemma. The realization that reality itself thrives on contradiction. When scientists first discovered this, it seemed impossible. Waves and particles belong to different worlds. A wave is spread out, continuous, indefinite. A particle is localized, solid, definite. To claim light was like claiming a coin is both heads and tails in the same moment. And yet, experiment after experiment forced this truth upon us. In the famous double-slit experiment, light creates rippling interference patterns when unobserved, as if it were a wave passing through both slits at once. But when measured, photons strike the screen one by one, as if they had always been tiny bullets. Observation itself changes what light appears to be. Reality, it seemed, had no fixed identity until forced to reveal one. But the paradox does not stop with light. Matter itself carries this duality. Electrons, protons, entire atoms behave like waves under certain conditions, spreading and interfering, as though solidity were an illusion. And yet, in other contexts, they appear as particles, sharp and definite. The boundary between energy and matter dissolves too. Einstein showed they are two sides of the same coin, convertible in the equation E equals mc squared. What looks like a rock and what looks like pure radiation differ only in form, not essence. Energy condenses into matter, and matter evaporates back into energy. This duality runs deeper than physics. It seeps into the logic of existence itself. Opposites do not cancel each other. They define each other. Light and darkness, order and chaos, creation and destruction, all are interwoven, each incomplete without its counterpart. Reality is not made of singular, simple truths, but of tensions, contradictions, complementarities. Just as a magnetic pole cannot exist without its opposite, perhaps no concept we hold can stand alone. Every truth carries its twin. The cosmic duality dilemma forces us to admit that our language, built on separation, may be too small for the universe. We like categories: wave or particle, matter or energy, being or nothingness. But the cosmos laughs at such divisions. It presents us with both slash and instead of either slash or. Reality insists on contradiction because contradiction is its lifeblood. Without it, there would be no dynamism, no becoming, no universe at all. Take life itself. We live because of the interplay of order and entropy. Cells fight to maintain structure against the constant pull of disorder, and in that struggle, consciousness emerges. We die because disorder eventually wins. Yet without that tension, life could not exist in the first place. Even at the level of time, the paradox persists. Every now is both fleeting and eternal, gone in an instant, yet always the only moment you can ever experience. The dilemma also touches philosophy. If reality thrives on contradiction, then truth may not be singular but layered. Something can be two things at once, depending on how it is approached. This is why quantum mechanics resists classical explanation. It refuses to collapse into a single human category. The cosmos is not waiting to fit into our tidy boxes. It transcends them, forcing us to expand our notions of what real means. And yet, there is a strange beauty in this. Contradiction does not destroy meaning. It enriches it. Light is not diminished by being both particle and wave. It is made more mysterious, more profound. Matter is not weaker for being energy. It is more powerful, more fluid. Reality is not broken by its contradictions. It is animated by them. To deny duality would be to flatten the cosmos into lifeless simplicity. To embrace it is to glimpse the richness of a universe that dances between opposites. So the next time you see a beam of light, pause. You are not just looking at illumination. You are looking at the paradox at the heart of reality. A contradiction that refuses to resolve, a riddle that refuses to end. The cosmic duality dilemma is not a problem to be solved, but a truth to be lived with. That reality is not either slash or, but both slash and. Light is wave and particle. Matter is energy. Being is contradiction. And it is within that contradiction that the universe finds its spark. Gravitational time dilation. Imagine two people standing in very different places in the universe. One near the surface of a massive star, the other drifting far away in empty space. For the one near the star, gravity pulls fiercely, bending not only space but time itself. Their seconds stretch longer, their heartbeat slows compared to the rhythm of the cosmos, though they never notice it themselves. For the one in empty space, time flows faster, unburdened by the weight of gravity. Both live in their own realities, each feeling normal, each believing their time to be absolute. Yet when they meet again, they discover the truth. They have aged differently. What they thought was simultaneous was never the same. This is gravitational time dilation, and it shatters the idea of a single universal clock. Einstein's theory of general relativity tells us that time is woven into the fabric of space, and that fabric curves under the influence of mass. Gravity is not a force pulling at you, but the bending of space-time around massive objects. And when space-time curves, so does time itself. This is not science fiction. It has been tested. Clocks placed on mountains tick faster than those at sea level. Astronauts in orbit age slightly more than those on Earth, because they are further from the planet's gravity well. Even satellites in the global positioning system must constantly adjust their time, or else your phone's maps would drift miles off course. Our technology functions only because we acknowledge that time is not absolute. It bends. It stretches. It is local. But the real strangeness comes when you realize what this means for simultaneity. The idea that two events can happen at the same time everywhere in the universe dissolves under gravity. There is no cosmic master clock keeping order. Instead, every region of the universe carries its own tempo, its own beat, its own version of reality. A soldier on Earth, a traveler near a black hole, a wanderer between galaxies. They all live in timelines that are not in sync. The deeper you are in gravity, the slower your time flows compared to others. This makes simultaneity impossible, not just practically, but fundamentally. To see this more vividly, imagine twins. One stays on Earth, the other travels near a black hole where gravity is immense. Hours pass for the traveler, while years pass for the twin at home. When they reunite, one is decades older while the other remains young. Both lived each moment naturally. Both believed they were aging normally. But gravity carved their destinies differently. It is not that one was right and the other wrong. It is that reality itself is fractured by gravity into multiple tempos of existence. The universe allows both truths at once, yet no single universal time binds them together. Philosophically, this idea is devastating to the way humans once imagined reality. For centuries, time was treated like a river, flowing steadily forward, the same everywhere. Newton believed in absolute time, universal and unchanging, ticking like the heartbeat of God. But Einstein proved this wrong. Time is not the same for everyone. It is woven with space, stretched by speed, warped by mass. The river of time does not flow evenly. It bends into whirlpools and slow eddies, depending on where you stand. There is no single now that belongs to all. There are only local nows, bound by perspective. This realization reshapes how we think about reality itself. If simultaneity is impossible, then even the idea of a shared present becomes questionable. What feels like now to you may not be now to someone else. Events in distant galaxies may already have happened from your perspective, but are still in the future from another's. The universe is not a single unfolding story, but a patchwork of overlapping timelines, stitched together by gravity and motion. We are all living in different rhythms, each real, each true, but never synchronized into a single absolute frame. And then comes the most haunting question. If time is relative, then what does it mean to exist together at all? When you sit with a loved one, you share a moment, but strictly speaking, your bodies experience time at slightly different speeds. The deeper the gravity, the greater the gap. On Earth, the difference is tiny, almost invisible. But near a black hole, it becomes cosmic. Imagine watching a starship descend toward the event horizon. From your perspective, their time slows to a crawl, freezing at the edge. To them, nothing strange happens. They cross the horizon in finite time. Both perspectives are true. Reality itself allows both to coexist, even though they contradict. The universe does not insist on one truth, but holds multiple truths in parallel. This is the unsettling gift of gravitational time dilation. It proves that time is not universal, not absolute, not shared equally by all. It belongs to gravity, to motion, to place. It tells us that simultaneity is an illusion of convenience, useful for human life, but broken at the edges of cosmic law. In the deepest sense, we are all separated not just by space, but by time itself. Your seconds are not my seconds. My minutes are not your minutes. Each of us carries a private stream of time, flowing at its own rate, connected but never identical. So when we ask, what time is it in the universe right now? The answer is simple. The question has no meaning. There is no universal now. There are only countless local nows, stitched into the vast fabric of relativity. And in that fabric, simultaneity is impossible. Time itself is not a single story, but an orchestra of rhythms, playing together, yet never perfectly in sync. Universe consciousness puzzle. Imagine stepping back far enough to see the universe not as scattered stars and galaxies, but as one vast interconnected whole. The same way trillions of cells make up your body, billions of galaxies thread into a cosmic web. And then ask yourself, if consciousness emerges from the complexity of the brain, could something as immense and interconnected as the universe itself also be conscious? This is the universe consciousness puzzle, a question that blurs the line between science, philosophy, and the limits of human thought. Because if consciousness is woven into the fabric of reality, then perhaps reality itself is aware. But here lies the paradox. The very act of trying to prove it collapses under our own limitations, leaving us trapped between awe and uncertainty. Consciousness is already the most mysterious feature of existence. Neuroscience can track electrical signals, map brain regions, and even correlate activity with thoughts. Yet no equation explains why there is an inner experience at all, why matter arranged in a certain way becomes aware. This is called the hard problem of consciousness. How subjective experience arises from physical processes. If we cannot solve it within the human brain, how can we possibly solve it at the scale of the cosmos? And yet, the question refuses to die. If consciousness is not just an emergent property of brains but a fundamental aspect of reality, then perhaps the universe itself, in its totality, could be conscious. Imagine a vast neural network. Billions of nodes, connected, exchanging information, forming emergent awareness. Now scale this up to the universe. Galaxies linked by filaments of dark matter, stars exchanging radiation, black holes shaping spacetime. The cosmic web resembles a brain in its structure, patterns of clustering and connectivity that hint at complexity far beyond chance. Some physicists and philosophers have asked, is the universe itself processing information? And if it is, does that processing give rise to some form of cosmic awareness? Not necessarily human-like, not emotional, but a vast and alien self-knowing that pervades all of reality. Yet the puzzle tightens. For if such a universal consciousness exists, how could we ever prove it? Consciousness is private. You know you are conscious because you experience it from within. But you cannot directly prove another person's consciousness. You infer it from their behavior, their communication. With the universe, we cannot step outside to ask. We are inside the system, like neurons inside a brain, unaware of the mind we may be contributing to. To demand proof is to demand a perspective we can never occupy. The paradox is clear. If the universe is conscious, we cannot confirm it from within, and if it is not, we cannot disprove it either. Some thinkers turn to philosophy. Panpsychism suggests that consciousness is not rare, but fundamental, present in every particle of reality in rudimentary form. In this view, atoms have proto-conscious qualities, which combine into greater forms, just as cells combine into organisms. Scale this upward, and the universe could be the ultimate mind. Others invoke information theory. If reality is defined by information, and information processing is consciousness, then perhaps the universe's information flow is itself a kind of awareness. Still others frame it spiritually, that the sense of being part of a greater whole is not an illusion, but a reflection of reality's true nature. But every path leads back to the same impasse. Consciousness cannot be measured like mass or charge. It resists instruments, eludes equations, refuses to be pinned down. And so the universe consciousness puzzle remains a riddle. To prove it would require stepping outside existence itself. To deny it risks underestimating the depths of reality. We are left in a twilight state, where certainty dissolves and only questions remain. Imagine if it were true. Imagine the universe not as cold machinery but as a living presence, aware of itself through the countless forms it spawns. Every star a flicker in its thought, every life a passing dream. You, listening to this, not separate from the whole but part of its vast awareness. The universe, in this picture, does not merely contain consciousness. It is consciousness, unfolding into countless forms. But if it is not true, then consciousness is a rare flicker in the dark, fragile and local, destined to vanish when brains decay and stars die. Between these two possibilities hangs the weight of meaning itself. The universe consciousness puzzle is less about finding an answer than about facing the boundary of human knowing. It is the recognition that reality may contain truths forever hidden from beings made of flesh and thought. That perhaps our role is not to solve every riddle but to live within them, to feel the wonder and terror of being conscious in a cosmos that may itself be aware. And in that humility, perhaps we glimpse the paradox's final lesson, that the mystery of consciousness is not a problem to be solved, but a mirror held up to existence, reflecting both the universe and ourselves. Infinite future void. Picture time as a road that stretches endlessly. You walk, and the horizon keeps moving, always ahead, never ending. At first, this idea of eternity feels like abundance. An infinite future, limitless chances, endless days stacked one after another. But stare at it more deeply, and the meaning starts to dissolve. If time has no end, then eternity is not filled with events, but with emptiness. If there is always more time, then every moment loses weight, every action loses urgency. Forever begins to look less like everything, and more like nothing. This is the paradox of the infinite future void. When stretched long enough, eternity becomes indistinguishable from never. Think of waiting for something important, an answer, a reunion, a final breath. If you were told you must wait forever, would you ever receive it? No. An infinite wait is no wait at all. A promise stretched into eternity is a promise broken. The idea of forever collapses into the same shape as never. To say something will happen infinitely far in the future is to say it will not happen at all. Time's gift, when extended without limit, becomes the cruelest absence. Now consider our universe. If cosmology is right, and time does not end, then the future stretches without horizon. Stars will burn out, galaxies will drift apart, atoms may decay, and all complexity will dissolve. What remains is an endless expanse of nothingness, a universe still existing, but empty, dark, silent. Time will continue, but nothing will fill it. What is the difference, then, between a billion years of nothing and a trillion, or an infinite stretch of void? The silence does not deepen, the darkness does not change. Eternity flattens into sameness. Forever becomes indistinguishable from never, because in the end, the infinite future holds no events, no moments, no distinctions, only endless absence. Philosophically, this strikes at the very heart of meaning. We anchor significance to finitude. A life is precious because it ends. A day matters because it passes. Without limits, choices blur. Imagine if you had infinite time to do everything. You could delay forever, and nothing would ever demand urgency. Deadlines would vanish, value would dissolve. A diamond's rarity makes it precious, but an infinity of diamonds makes them worthless. In the same way, an infinite stretch of future does not amplify meaning, it erases it. But this paradox grows even sharper when we reflect on eternity in spiritual or religious terms. For millennia, humans have dreamed of immortal life, of heaven, of forever. But if existence never ends, what then? Do joy, love, and fulfillment retain their brilliance after infinite repetition? Or does the very promise of eternity flatten into monotony, until it feels no different than oblivion? Forever may not be the bliss we imagine, but a void of sameness, a horizon that consumes difference. And if forever equals never, then perhaps immortality is not paradise, but prison. Consider a candle. Its flame is beautiful precisely because it flickers, because you know it will end. The shadows it casts matter because they are brief. Stretch that flame into eternity, and it ceases to flicker, ceases to matter. It becomes a constant glow without beginning or end. After infinite time, you would not even notice it. The candle's eternity would be indistinguishable from its extinction. Even mathematics whispers this truth. Infinity is not a number but a concept. Add infinity to 1, or a billion, or a trillion. The result is the same. Infinity. No matter what you place into the boundless future, it is swallowed. A moment, a century, a civilization, an entire universe, all reduced to the same insignificance against eternity. The infinite future void does not preserve meaning, it devours it. And yet, here we are, finite beings with finite lives, staring into the abyss of infinite time. Perhaps the paradox is not meant to depress us, but to awaken us. If eternity collapses into nothing, then the only time that matters is now. The only real forever is the fleeting moment you hold. To chase immortality is to risk losing meaning. To embrace finitude is to uncover its weight. Our mortality, our limits, are not curses, but the very condition that makes anything matter at all. So when we imagine time without end, let us not envy it. Let us see it for what it is, a void dressed in abundance. Forever and never are twins wearing different masks. And the paradox of the infinite future void is not a mystery to solve, but a mirror to remind us. Meaning is carved not from eternity, but from impermanence. In the end, eternity's silence teaches us to treasure the fragile music of now. For when time has no end, forever is indistinguishable from never. And the miracle of existence lies not in how long it lasts, but that it happens at all. Last observer paradox. Close your eyes and imagine the far future. Stars have burned their last fuel. Galaxies have dimmed into cold islands of dark matter. Planets drift barren through empty space. Black holes evaporate into whispers of radiation, until even they are gone. In that final silence, no life remains, no eyes to see, no minds to ask questions. Here lies the last observer paradox. If life ends, does the universe continue unobserved, or does unperceived reality vanish into nothingness? At first, the answer seems obvious. Of course, the universe continues. Mountains do not crumble when no one looks at them, and stars do not blink out when unmeasured. Surely reality is independent of perception. But physics complicates this comforting belief. At the quantum level, particles exist in superpositions, clouds of probabilities, until measured. Observation forces the wave function to collapse into definite reality. Does this mean that without observers, the universe itself remains in some strange, undefined state? If there is no consciousness to measure, does the cosmos return to an uncollapsed haze, a silence of probabilities? This idea haunted the founders of quantum theory. Niels Bohr and Werner Heisenberg argued that observation is inseparable from reality itself. To measure is to define, to collapse possibility into fact. John Wheeler went further, suggesting a participatory universe, where reality requires observers to exist at all. In this view, consciousness is not an afterthought of the cosmos, it is its partner. Without it, the universe would be mute, unformed, an unfinished equation waiting for someone to read it. Yet others resist this notion. They argue that the universe has been around for 13.8 billion years, long before humans existed, and surely it was as real then as it is now. Dinosaurs did not need physicists to walk the earth. Stars did not need eyes to ignite. Reality, in this view, is objective, indifferent, unshaken by the absence of minds. The cosmos exists even when no one looks, and observers are incidental, brief flickers of awareness in a vast, impersonal expanse. The paradox deepens when we ask, what does it mean for something to exist unperceived? If no one is there to witness, can we say the universe is real in any meaningful sense? Existence without observation becomes a kind of ghost reality, silent and inaccessible. Philosophers from Berkeley to Kant have wrestled with this problem, asking whether reality is independent of mind or inseparable from it. The last observer paradox forces us to confront this question not abstractly, but cosmically. Consider a thought experiment. Imagine a book locked away forever in a sealed vault, never to be read by anyone. Does the story inside exist as story, or only as ink on paper? Without a reader, is the meaning there at all? The universe may be that vault, and observers are the readers. Without them, is there still a story, or only empty symbols? The paradox takes a darker turn when tied to the ultimate fate of life. If consciousness is required to collapse reality, then the end of life is the end of the universe as something real. Without minds, existence becomes a hollow potential, unmeasured, unspoken. But if reality is independent, then the cosmos will go on, vast and indifferent, a play without actors, a stage without audience, forever performing to no one. Both outcomes are unsettling. One leaves us with the thought that existence itself dies with us, the other with a universe eternally alive yet utterly meaningless. And perhaps this is the true weight of the paradox. It places us at the center of reality while reminding us of our fragility. If observation is essential, then consciousness is not trivial. It is cosmic. If observation is not essential, then consciousness is irrelevant, a spark in the void, gone without consequence. Either way, the paradox confronts us with a truth both humbling and terrifying. The meaning of existence may hinge on whether reality requires witnesses. So when you look up at the stars tonight, ask yourself, are you giving them existence, or are they giving it to you? Are you the final piece that makes the cosmos real, or just a fleeting moment in its endless play? When the last observer falls silent, does the curtain close on reality itself, or does the universe continue, unmeasured, unperceived, whispering into an eternal void?